My name is Bianca. What should you know about me? I'm a JavaScript developer. I work as a consultant, so I go into mostly enterprise companies and help them with their JavaScript. I also work on open source. Part of our company, we have an open source framework called CanJS, so I do work on that as well. Today, we're going to talk about algorithms. Like Mark said, this is part of a 4-class series on data structures and algorithms. So this is the sort of foundational knowledge, and as we move along the series, we're going to build on these topics. So we're going to talk about the algorithms only today, no data structures today, aside from like maybe an object or an array. And then next time, we're going to go over some common interview data structures and algorithms, and then we're going to apply this stuff. So this will be a prereq to the following course. And we'll apply these algorithms to some common data structures, to some common interview questions. And then the next part, part 3 and 4 is all trees and graph theory. So as web developers, that's so important. So we're just 2 days doing all of that, traversing, sorting, balancing, all of that. So that's sort of the higher level progression of this course. So today's algorithms. So what is an algorithm? Why should you care? So algorithm is just the steps that you take to solve a problem. Why should you care? You're an engineer. It's your job to solve problems. When we learn about algorithms, we're learning different techniques to solve problems in a certain way. We're identifying patterns, and we're applying algorithms to those patterns to get a result to improve the speed of our programs. Okay. So what are we going to cover today? We're going to cover a lot. So we're going to discuss really informally how to generally estimate an algorithm. We're not going to go into mathematical proofs or anything like that, but we're going to talk about little things that you can spot to start to reason about the time complexity of an algorithm. Then we're going to talk about a couple techniques for optimization, which are fun. We're going to get really comfortable with recursion. How are people feeling about recursion right now? Feeling good? Okay, cool. Well, you're going to be like, man, I think most of this course is like recursive algorithms and going through recursion in a bunch of different ways. So if you're feeling like this, you'll probably be like this at the end. If you're feeling like this, you'll probably be here. So that's fun. And something, it's like such an abstract thing. It's hard for a lot of people, so I like to focus on that because that's the foundation of a lot of algorithms, and then we have recursive data structures as well. So we're going to do a couple sorting, a couple searching. I'm not going to go through the exhaustive list of every sorting and searching algorithm because, snooze. But we'll go through a couple and focus on the implementation of them rather than the theoretical aspects of sorting and searching. If I have time in a future course, I might go into that, but we'll see. I don't think it's the most important thing to understand, like, what are the trade-offs between bubble sort and insertion sort, because, at the end of the day, when you get into your interview, you just need to know one, and you know what I mean? So, sure. We're going to talk about also the divide and conquer technique and dynamic programming. You might see these and think, okay, recursion, you're right, recursion, more recursion. Same with sorting and searching, recursion. And then we're going to talk about the greedy technique and my opinions about the greedy technique and how you should apply the greedy technique to interviews. And then we'll also talk about brute force as well, recursive brute force. Any questions about all of this? Cool. So it is a lot. There are corresponding exercises for each of these topics. Probably not going to be able to finish them in class today, just because I want to get through a lot. But you should have a solid attempt for most of them. And then we can be in touch after class if you need help with anything. And online folks, too, you can always tweet at me or email me, your exercise solutions if you're, you want feedback or you're stuck or whatever. Happy to do that. We're going to talk about time complexity. Time complexity is how we reason about the speed of an algorithm. So as you can imagine, speeding up an algorithm allows us to process more and more data inputs. However, we can't time the start and the finish of an algorithm, so we use a way of estimating the speed of algorithms, right? So if we run some code on a machine, there's a lot of factors that we can't control, such as the speed of the machine, and the language that the environment that the language is executing in, and all of these things. So instead of saying this algorithm is 3 seconds long, we say that this algorithm, as the input grows, it will grow in this proportion. And so we're going to talk about that a little more in depth. So there's two things. There's space complexity, which talks about how much memory is used. And there's time complexity, which tends to be a little more difficult for people, which is how many operations are executed to solve your problem. So, and we want to think about this in respect to input size. So as your input grows, how many more operations do we have to complete? And we also are pessimists in our field, and so we always want to assume the worst case scenarios. And so we're thinking about always worst case scenario, and yeah, but there are other ways to think about it as well. Okay, questions? No questions. Okay. All right, so let's look at a few examples. So here is kayak.com. Let's say you're an engineer here. Your PM or your whoever is telling you what to do says, okay, given this list of hotels, you need to return the minimum and the maximum price value for all of the results from some search query. So how might we solve this? Cool. So, one note, so as more data is being processed, so say we have a list of 3 hotels versus a list of 1,000 hotels, you would expect, right, you're going to be doing more operations. That's the obvious part. So that's why we like to think about it in terms of proportion. So as you're adding one, how many more operations need to be completed to get to your solution? And the cost, as a result, as your data set grows, the cost can either be really great or it can grow really slow. All right. So one approach to find the range is we simply have some nested loops going on, and we compare all numbers, all prices to the other prices. And so you can imagine that we won't compare one to another, but we say, okay, so is 50 greater than 200? No, or we'll just keep track of that. And then we compare, keeping track of the lowest and the highest. As we're looping through, we have some variable that we're updating. But we have some nested loops because we want to make sure that we're comparing everything to everything. And so you can see every time we do this comparison, and we are doing some operation, right, which is the greater than or less than operation. And so every time our list grows, so say we have 3 items, kind of like this graph here, right, we're going to do 9 compares. Versus if we have 5, it's definitely 25. Because our table is going to grow. As we compare numbers, our x and y's will compound. So 10 is going to be 10x, 10y, and so there will be 100 comparisons. And so this is what we call quadratic time. So as our number of n, which is the number of hotels, increases, our number of operations increases by the power of 2. So 3 times 3, 5 times 5. 10 times 10. And this is how I want you to think about time complexity. As our input grows, how much more work do we need to do? Okay, here's another approach. What if we have two loops? On the first loop, we check what's the minimum. In the second loop, we check the maximum. How many operations do we need? So for our first loop, we say, is 200 the maximum? Yes. Is 50 the maximum? No. So we'll just keep 200. You can imagine we might do that a bunch of times. Is 175 the maximum? No. We'll keep it at 200. And then we have another loop. It's going to loop through. Is 200 the minimum? At the very first point, yeah. And then is 50 the minimum? Yes. Now it's the new minimum. Then we keep going. And then 50 is still the minimum. And so in this technique, we are searching for each, or we are looking and doing operations on each item one at a time. So this is two loops, not nested. The first example, nested loops, where every item gets compared to every other item. This one, every item gets looked at once. We just keep track of that min, and then we look at it a second time, and we keep track of that min. And so how, if you had to put this in terms of n, I'll give you the answer. I always do that. What do you think, if you had to guess? So if the other one was n squared.
2 times n?
Yeah, 2 times n, exactly. So for the first loop, that's n, right? So from 0 or 1 to 3. The second one, 1 to 3. Cool. And so, yeah, so every time we increase n, our work increases by 2n. Questions here? Is everyone clear on the difference between 2n and n squared? Okay.
It's just shorter.
Yeah, it's faster. Less comparisons are made. And you can make this table, and you can see that this one only has 2 here, and this row here is n, or the number of hotels. All right. So what if the list was already sorted? How might we find the min and the max there? How about, who do I want to choose? So many people. I like all of you. How about Josh?
Oh, I missed the first part of that.
Yeah, so if the list was sorted, how might we find the min?
If it was sorted, well, there's that thing where you just divide it and then you divide it or whatever into chunks.
That's true. That's if you're searching for something.
I guess one end, you just go through the list and.
But if it's sorted, you know the minimum is where.
Or you just go to the first.
Yeah, exactly. So we just know exactly where it is. So we'll go to the first one. And Sarah Rose, what about the max?
Well, you'd go to the last one.
Yeah, we just go to the last one. So that speeds things up considerably, right? No loops, definitely no nested loops. And so every time, you know, the number of operations is really, no matter what, no matter how long the list is, it's still going to be, I would say 2.
Yeah, why is it 3? I was going to ask.
I don't know. There might be something else in here.
Because it's sorted?
It has to sort.
No, it's already sorted. Because the sort, if there's a sort on there, then the time complexity would change. This is the correct slide. Okay, so if it's sorted, we just do 2 operations, no matter the length of the array. So we can have a list that's 100. It's still, we get the first, we still get the last. And so the number of operations doesn't change. Cool. Questions? And here's just a review of that. So if we compare all the numbers to one another in that nested loop situation, the very first one, that's going to be n squared, because as our n increases, each loop is also going to increase. And so we need to multiply it by itself. Anytime you have one loop, and it's looping from the beginning to the end of n, that's going to be just n, right? Because when it's 10, you loop 10 times. When it's 11, you loop 11 times, right? And so 10 is n, 11 is n, so we just have n. And in this case, we have 2n because we have one loop, and then we finish that loop, and then we do a second loop, and we finish that loop. They're not inside of each other. And then with just the 2 here, we just go directly to the source, right? Either the beginning or the very end, because our list is already sorted, and that's nice. Cool? All right. Here's some fancy names for these things. So when we say n squared, that's called quadratic time. We talk about time complexity using something called big O notation. And so we would say, this is O of n to the 2, or O of n squared, or quadratic time. That's how we talk about it. And then we say O of n, which is linear, for our 2n example. And then O of 1, constant time, for our, this is another correct slide, sorry guys, for our case where we're going directly to the min and the max here. Cool. So the next logical question might be like, what's with these 2's, this one says 1, that one just says n, but we have 2n and we have 2. When we are thinking about time complexity, we don't think about every small detail. We want to have a big picture estimation, and so we drop what we call non-significant numbers, which is anything that is not pretty much listed here. So if it's not n or log n or n squared or k to the n, we just drop it essentially, and we just give it a big label versus getting into the nitty-gritty of, if you take an algorithmic analysis class, you will do all of the calculations that go into this, but in the interview setting, it's not expected that you're going to be proving this. So you could just think about it like that. And what else do I want to tell you about this?
Bianca, is this the entire range of the big O notations?
Yeah. More or less. Yeah. It's the major ones, but there's also n log n, which is another major one, which is linear times logarithmic. But we'll get to that when we get to merge sort. We'll talk about that a little bit. But good question, thank you. Oh, and also the fastest algorithms are in constant time, and the slowest are in exponential time, right? So as this input grows, it's like an exponent. It grows exponentially, and this one grows, n times n. This one grows just by n, so it kind of is like a straight line, or not a straight line, but a straight diagonal. And then we'll talk about logarithms in a second. And then constant is always going to be the same. No matter how your input grows, it's always going to be the same number of operations. Okay. Here's a graph. So here's our constant time, right? It's no matter what, it's always going to be the same. Here's some exponential ones. Here's a cubic one, quadratic. These are all really, really, really slow. Look how fast they grow as the input grows. So when your inputs are sufficiently large, you just can't compute anymore. It'll take like 1 billion years, and you won't be able to solve your algorithm. And that's why it's important to know how slow it is or fast, and then be able to reason about how to speed it up or understand the constraints that maybe you can't do that, and you might need to make some trade-offs, like maybe algorithmic correctness, which is this idea of that, is your solution to the algorithm the optimal solution or the correct solution. Sometimes you have to make a trade-off because your algorithm otherwise would be so slow that it would never compute. So it's like better to have some solution that's good enough versus no solution at all. What else? Oh, and then we'll talk about logarithmic in a second, but what it's good to know is that as log grows, you can see that this is really steep at first, and then it tapers off. So as a logarithmic solution, as the inputs grow for a logarithmic solution, it grows, but then it kind of tapers off. So as the work increases, the delta or the increase lessons. We'll talk about that more. Yep.
So it looks like there are some places on the graph where the quadratic is actually more efficient than the logarithmic, like if you had a very small data set. So would there ever be a point where you might choose that over the other?
Usually,
efficiency,
like,
or
time complexity isn't so important when your data
set is small?
set is small. So I would just, if your data set is small, I would just focus on readability rather than performance. When your data set is large is when you want to start thinking about the speed. Really, you don't want to start thinking about speed until, like it's lagging, and someone's complaining about it. You don't want to pre-optimize, but yeah, you really don't need to start thinking about it until your data set grows and there's some sort of lag in your computation. But it's a good question. Let's talk about some native JavaScript methods, expressions, operations that you see, and talk about what the time complexity of each one is. So what's a method? Like, think about like array methods or what's that? Yeah. Yeah. That one's a little complicated though. We'll save that one. That's another good question.
For loop.
Pop.
Who said for loop?
For loop.
Yeah, so for loop, we talked about that a little bit, is what? Linear, right?
Yeah.
So if you have a for loop, it's whatever the ending case, which is like usually say like I is less than n, and whatever n is, that is going to be the number of operations, the number of times that loop executes. Good. And then what did you say, Matthew?
Pop.
Pop. Yeah. So pop is where we remove. Oh, I should do. Where we have some array 1, 2, 3, and we say array dot pop, which just removes the last one, and then oh my goodness. 1, 2. So pop is a constant time operation because you're always taking off the last one. Always taking off the last one. Cool. What are some other ones? So we have pop.
For each, as complicated as the map.
Well, I guess, so the thing to know about for each and map is that under the hood, they're just loops. So it's very similar to the for loop. It just gets a little hairy because you're passing a callback in there, and based on what is inside of that callback, it can vary the number of operations. So if in your for each you pass a function that also has a loop in it, then it's going to change. So that's why it's a little complicated, because there are some other factors. Like pop will always just pop off the last one, and that's not, there's no other variables to consider. Okay. What else? How about Patrick?
So let's say you want to get the first value in the array. Can you do a for loop that just always get the first value? Would that can still be constant?
Well, anytime so you wouldn't actually need to use a for loop. If you want to get the first one, you can always just reference the 0. And this would be constant. So just like in our min-max price range example, when we had the sorted list, just go directly to the index. And you can imagine, like if you're a visual person, that there's like this array, it exists in memory, and then there's like some mathematical formula to calculate like where like your needle that's going to read it is going to like land in your hard drive. This is not exactly how it works, but you can kind of imagine that's why it's constant time. So when you have a when you have an index, you can imagine that there's some formula that's like 2 plus 2, or 2 plus index, multiplied by the memory address, or something like that, and it knows exactly where to go. It doesn't have to like search through all of your data in your hard drive to get to where it is. Or actually, in this case, it's in memory because this is not a database. So that's why this is constant time. And this, like, you don't need to start at array 0 to get to array 1. It just goes directly there. I just like imagine like this big needle reaching in and like pointing and like, there it is. But that's just my active imagination. Similarly with an object, so if we have some object, right, and we're doing a property lookup, you can imagine that it's doing the same thing. So it has some formula, and it just goes right to where it needs to go, constant time. All right. What about this? As your inputs grow, 1 plus 2 will always be 1 plus 2, assuming that your input isn't, like these numbers aren't variables, right? Or actually, even if it was, 1 plus n is always just going to be one operation, right? Just addition. Okay. So math is constant. Our lookups are constant. What else? Saving to an object and array, you can think of it as constant in JavaScript. Any other common methods, expressions, operations? We talked about the greater than and less than. That's a constant time operation. So when you're looking through your algorithm, you can kind of spot these things and think about, okay, as my input grows, and you need to also pay attention to what is your input, right? Because there could be a few different variables. Like you can have a list and you can have a number, and we'll talk about that when we go through some examples. But as your input grows, how is it going to change, right? So if you have an array and you pop one off, if the array is length 3 or the array is length 1000, it's always just going to pop off the last one. That's just constant. It's not changing when your input changes. However, if we do something like unshift, unshift, or why am I blanking? What's the other one? Where you
Bush.
Slice.
no.
Splice.
No. So when you put something on or take something off the front of an array. So shift and unshift. Oh. Okay. Shift and unshift. What the difference there is that shift and unshift are not constant time operations because you need to, so if we're starting with 1, 2, 3, we want to shift a 0 on the front. We have to first, so we put the 0 here, but then we have to move the 1 to the next one. Then we need to move the 2 to the next one. Then we need to move the 3 to the next one. And so if our array is size 3, we have to move things over 3 times. If our array is size 100, we have to move things over 100 times. So what is the time complexity of that?
Is that actually how they do it?
Quadratic.
Mm-hmm.
Okay.
What is it?
Quadratic.
Close. So if the length of the array is 3, it's 3. If the length of the array is 100, it's 100. Linear. So it's just n. So if n is our length of the array, it's going to be linear. Mm-hmm.
So then, kind of like a native method that uses kind of a combination of both of these that you've talked about. What about something like reduce that has all of these different, can expand, but then also you're contracting through adding
Yeah.
and addition as well?
Yeah, so that's another one that takes a callback, and the time complexity of reduce, like in its core, it's really just a loop that's calling a function with some arguments, so that's linear time. But when you're taking a callback, you need to consider the time complexity of that function that you're passing into reduce. So if you have a constant time operation in reduce, like the classic example of reduce is like adding 2 numbers together or something. That's constant time, so that's really not going to change anything, so it'd still be linear. But if you're doing something more complicated inside of that callback, it can increase the time complexity significantly. So, yeah, good question. These are good questions. No one's ever asked me about, I guess the last time I taught this class, like map and reduce and for each weren't that popular yet. So this is good. This is good.
Someone online asked about sort.
Okay, so that's a good question. So sort under the hood is, it really depends. Dang it, this is a hard question. We could just say that it's n log n, which is something that we're going to talk about when we get to sorting. I want to put all my cards on the table. So what if we have multiple expressions or we put them inside of a loop? Like, how do we reason with a function that in the function body has multiple expressions? And so if the way I think about it is if you have multiple expressions that are not inside of a loop, I just add them together. So if we have a bunch in constant time, I would just say like 1 plus 1 plus 1 equals 3. However, if these things get put inside of a loop, then you start to multiply it. So if you have a loop inside of a loop, right, we have n, a loop is linear, right, we talked about that, and then we have a loop inside of a loop, it's n times n, which is then quadratic. If we have 3 loops, n times n times n. However, we also need to think about what is going on inside of those loops. So if inside of the loop we're doing like recursion, you know, that can add some more things. And so depending on the time complexity of that method that you're calling, you need to just multiply it by n inside of a loop. Otherwise, just add it. Does that make sense? Questions about this? Okay, so what about O of log n? So logarithmic time. So we don't really talk about logarithms anymore after, like, I don't know, high school or something. Unless you're a scientist, I guess logarithms are really important if you deal with like really big numbers or really small numbers, which is what we do, right, when if we're analyzing large sets of data. I'm not going to teach you logarithms right now, but all you need to know really is that logarithmic time, so logarithms can have different bases. You can have base 10, you can have base 2, and you can think about as your input increases, the work or the number of operations that need to be done decreases by a fraction. So commonly, if you are looping through an array, you have a loop, and then every time you loop, you cut your problem in half. That is going to be a logarithmic time. So every time you loop, you only have to do work on half of your data set, or a third, or some fraction, right? So logarithmic can be some fraction. So base 2 will be divided by 2, base 3, 3, 10, etc. So as it increases, the difficulty, or the time complexity increases at a fraction. So it grows really, really slow, which is good. Which is why it's pretty close here to constant time, and it's often better than linear time when we have a large enough data sets that we care about this kind of stuff. So that's what you need to know about log n. Cool. And then there's also n log n. N log n happens when you have a loop, and then you're also you have a linear loop, and then you're also looping and cutting it in half. So linear, and then you're cutting it in half, and you multiply them together to make n log n. And we'll see an example of that later. So you'll put some examples to these like vocab terms. Okay, questions?
So you mentioned different bases, and how is that determined? So it says base 2 or base 10.
It's what you divide it by. So if you're dividing your input by 2, then it's base 2. If you're dividing it by 10, it's base 10. Typically, you're gonna see it divided by 2, mostly.
Kind of like a binary search.
Yeah, exactly. Binary search, anything where you're cutting it in half. Okay, so here's a little table to help us have some reference. So if we're just running a statement, like returning a value, for example, is constant time. Any sort of value lookup, array object, variable is going to be constant time, again with the needle, just going directly to where it is in memory. Easy. So loop, you can think of this as a loop that cuts the problem in half every time. N is just going to loop through all of them. So anything where you have to look at everything at least once is going to be at least N, right? So N squared is going to be double nested loops. And then we have triple nested loops of n to the 3, or n cubed. So just a word of caution. I'm giving you some tools to make rough estimations here. This is not the full version of how to calculate time complexity, which is deeply mathematical and really out of the scope of this workshop. But what you need to be mindful of is what is n, because you're going to have a lot of different data points in your methods or in your algorithms. And so you want to make sure that you're identifying like what is the data set that's growing. And if you have more than one data set that has a variable length, you're going to need to take that into consideration. That's something that when people get started with this, they just assume that n is always going to be the length of the array, or n is always going to be, you know, a certain input, and it's not necessarily so. You need to really think about how your code is executing and what is changing as your input changes.
Can you provide a concrete example
Of what
what
exactly?
you're describing?
Of what I was describing. So like when they're, I will in our future slides.
Okay.
Yeah. Yeah, and when we go through it, I'm going to ask you, okay, what exactly is in here? And we're going to think about like, what are the things that are changing? Because that's one of the common mistakes, is assuming that n is a particular thing when it's not necessarily a particular input. Space complexity. I'm going to pass the mic to you guys. So given our conversation about time complexity, what do you think space complexity is all about?
How much memory?
Dealing with like stacks and queues possibly.
Mm.
I'm not super familiar, but
Yeah. So space is good. Yeah. So stacks and queues, those are data structures, and it's all about the space that it takes up in memory, right? So if your algorithm is copying your array a bunch of times, right, and you're making a new array, then in memory you're having like 5 arrays, and that's you know, a certain amount of space complexity. And it works on the same scale of constant, linear, et cetera, as time complexity, except that instead of the number of operations that are being executed, we're thinking about how much more space are we taking up. So are we, for every loop, creating a new array? Okay, so that's like the, you know, n times the length of the array of space every time. Or if, you know, we're sorting, what we call sorting in place, where we don't make a new array, and then our space complexity is constant, even though our algorithm's time complexity could be something totally different. So things to think about when you're thinking about space complexity is, are you making a new data structure? How often are you doing it in comparison to your input? And also with your call stack. If you're doing recursion, that's another thing to consider, is that that stack is also taking place in memory. However, that's not something you probably need to go in depth about in an interview. Just be aware to just mention that when you're talking about space complexity with recursion. And we're going to go through a lot of recursion, so we'll see that in action. All right. So here's some words, lots of words. Something that you should know from this slide is that there are other notations. We just typically use big O notation, which is the worst case scenario, but there's also like the average case scenario and the best case scenario, and all these different ones, and you can learn about it by following that link. However, in interviews, it's expected that we speak in the pessimistic big O notation. What is the worst case scenario of this algorithm? This is just a review. Worst case scenario, we're going to drop any non-significant operation or constants. Break. Here's another chart excuse me. Here's another chart on big O complexity. And you can see that we have our constant time and our log n times are very, very good. Then we have our linear, which grows at a much slower pace as well, also very good. And then as we increase to quadratic and exponential time, those are terrible, terrible, terrible algorithms. Another good resource, if you want to like learn more about this, is called the Big O cheat sheet, where I stole this image. And they have like the time complexity, there's the average, and worst cases for a bunch of different things. And you can even get a poster, so it's kind of cool. Really good resource. All right. So let's do an exercise together. We're going to reason about the time complexity of a few different functions. So this function is called the count character function. We loop through the length of a string, and then we increment a counter. So when our length of the string, which is n, right? So our n here, the thing that's going to change is the length of the string. And we know that because it affects the number of loops for our loop here. And then when we do an increment, that is going to be a constant time operation. So what do we think? So we have this constant every time. So if string is length 5, how many operations does this do? Just one, yep. How many operations does this line do?
1.
5.
5.
Oh.
For loops through
Yep.
the number of.
Yep, so this will be called 5 times. And then what about this one?
1.
Just once, yeah. And so we can say these are both constant time because it's going to be 1. Because when we, so let's make this really long, walking like really fast or something. How many operations for this one?
Still 1.
Still 1. How many operations for this one?
14.
Yeah, however long this is, right? And then this one?
1.
1. So what kind of time complexity do you think this algorithm has?
Linear.
Linear, right? The big giveaway is that we have this loop. And we're doing a constant time operation in the loop. So we just drop those. It's not that important. We stick to the linear. That's the most significant. That's the slowest part of this. So we don't really think about the constant.
Question. So it sounds like then when you assess it during the analysis, you evaluate every expression, and then whatever is the longest, what's the worst case, and that really becomes your
Yep,
time complexity.
absolutely. Yeah, exactly.
So it's not like holistically you assess it. You really like break it down into each expression, and then pick the worst one.
Yep, exactly. And then you learn to kind of like disregard certain things, like just, initializing values and returning values. You learn just to like, those don't really matter. And then you can kind of see where to focus your attention when you're estimating time complexity. So what is n in this case?
1. Right?
Constant?
Yeah, 1.
Well, what is the, so n in this case is the length of the string. And then the time complexity is going to be, as the string gets longer, how much more work do we need to do? So when the string is length 5, how much work does this expression have to do?
But didn't you say return is always going to be constant?
Well, the return, but what about this?
It needs to count.
Well, how does it get the length?
Yeah, exactly, Lainey. That's the exact point. How does it get the length? We need to understand the length property. So if the length property looped through the length of a string and counted from 0, to n, that would be a linear operation. Luckily, JavaScript's a little bit smarter than that, and we just keep track of the length. As we add items to our array or we remove items, we increment and decrement our length. And so the length is just a property lookup, right? So we have the dot notation. This is just, string. Everything's an object in JavaScript, and that's why we can do a property lookup, and that's going to be constant time. And as a result, this will always be a constant time algorithm. Which means if our string length was 1 million, it wouldn't be any slower than if it was just 1.
Because it already knows that.
Yeah, exactly. It doesn't matter. What about this one? So we have a list of different ways that you can greet someone in languages. What's the time complexity of push? We talked a little bit about that. Constant.
As long as it goes to the end.
Mm-hmm. Yeah, we always just put it at the end. Not a big deal. Other languages, you know, when you're actually doing like memory allocation, this might not be constant, but in JavaScript, we can reason that this is just constant. We don't need to worry about initializing an array of a certain length and blah, 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 and then keeping track, and then expanding if it exceeds a certain length. So we don't need to worry about anything like that. Cool. And then if we do, I always get these two. I never actually use these. Does anyone actually use these in their real life? Shift or unshift? So if we're taking the first one off the front, how does that change the time complexity of this operation?
Linear.
Just like I said, we are going to, if we take the first one off, then we need to shift the second one into the first, the second to the first, or sorry, second to the first, third to the second, fourth to the third. And then that's going to be n number of operations, where n is the length of that array. So we talked about speed. Are you guys ready to make it faster? Let's check our time. OK. So what is the time complexity of this algorithm? So this algorithm returns if an array is unique or not unique. It does so by comparing each item to one another. So we can spread this out a little bit. So we have our first loop, it's looping through the length of the array. We have the second loop, it's looping through the length of the array.
Is it n squared?
Quadratic.
Yeah, exactly, quadratic. And we can see I have some console logs here so that we can see where n is 3. We have, you know, at least 9. So we start with the outer loop, then we do the inner loop 3 times, outer loop, inner loop 3 times. And so that's going to be 9. 9 steps, more or less. Cool. All right, but we can do better. This is our first technique. I call it the breadcrumb method. I'm not sure where I got that from, to be honest. It could be very common. It could also just be something I made up. But essentially, what you do with the breadcrumb method is that you're keeping track of things that you've already seen. It's also called caching, right? So once we see something, we save it. And then we can do a property lookup on an object, which is what? What's the time complexity of a property lookup? Which is a constant time operation. So instead of having to do more work, again, we just take a look. So in this case, we're going to do one loop through the array. And if we have already found it before, so if we haven't found it, let's start with that, we're going to save that value to the object and set it to true. And so the next time we run into that, we simply check, this is a constant time operation, check if we've seen it before. And if we have, then we know it's not unique. Versus the first method where we have to have 2 loops, we are comparing each one to one another. That's going to be quadratic time. When we use the breadcrumbs technique, we could take a quadratic time algorithm and make it linear. And so huge gains in performance. Something that essentially can't even ever be completed, and quadratic time is so slow, to something that's pretty easy to manage with a large data set.
Is it common nomenclature to refer to it as breadcrumbs? Or is it just like your favorite?
I don't know. Like I was saying, I'm not sure where I got that from. Have you ever heard of it called breadcrumbs? It's caching, but I call it breadcrumbs because I like that mental image. And then we can see here, inside of our loop, we're only looping 3 times. whereas before we were looping multiple times. Cool. So easy optimization. We're just going to cache the result. So now it's your turn. Your goal here is to transform this simple sorting algorithm into a unique sort. So a unique sort takes an array with duplicates, removes the duplicates, and returns the sorted array. And so the sort is happening for you on line 10. You don't need to worry too much about that. This method here, or this function here, means that it's going to be returned in ascending order. If you want it to be in descending order, you just swap these. And the reason we have to do this is because the JavaScript native sort sorts, it's like a string sort. And so like if you have 1, 2, 3, and 12, it'll do 1, 12, 2, 3. And so that's why we need to pass this callback to tell the sort that we want to actually operate on this kind of comparison, which is a greater than or less than comparison. Okay, so you should be able to edit this directly in the slide. You can also open it in Replit, and then you can fork it, and then you can save them if you want. And you can have a copy of all of the exercises that you've worked on in your solutions in your own Replit. You will have to make a Replit account though. All right, so let's take a look at our solution. So we're going to use the breadcrumbs method, which is a way of caching values so that when we can keep track and remember values that we've already seen. And this method has a trade-off between, it speeds up our algorithm, but it does something with our space complexity. So as n grows, we are caching more values to our breadcrumb object, which means that we have a linear space complexity that we need to consider with this algorithm. So we're doing a trade-off time for space, which in most cases is fine, but it's just something to be aware of. So our task was to take a sorting algorithm and turn it into a unique sort algorithm, which means that we want to return an array with no duplicates. And so you can see our demo data here has a bunch of 2's in it, and we simply want to return 2, 3, 4, and any duplicates we want to ignore. So how are we going to go about doing that? So first thing we're going to do is we're going to set up our breadcrumbs object. Here you can also call this cache if you want. And this is where we're going to keep track of all values that we've seen before. If we've seen it before and we come across it again, we know that we don't need to push that value to our result. So we'll start our result off here, right? And this is another thing to keep a note of in terms of the trade-off between time complexity and space complexity is that we're creating a brand new array here. So not only are we creating an object, we're also creating an array to push into all of our results. There are other ways that you can do this without pushing to a new array, but this is the easiest way to get started, but just keep that in mind. So the first thing we're going to do is we're going to loop through the length of our list, and we are going to check if we haven't seen it before. How do we know we haven't seen it before? It's because when we look up array at I, so I is going to start at 1. Right, we're just assuming the very first one is not a duplicate, right? So we're going to start the second one, which is going to be this 2. So array at 1 is actually 2. And so if we do a lookup of breadcrumbs with the key 2, what is it going to return for us at this point, where I is 1, our very first loop? At this point, so I is 1, we haven't actually saved anything yet to our breadcrumbs. So it's the very first scenario. So we initialize it as empty, and so we're saying what is breadcrumbs at 2? It's going to be undefined because breadcrumbs is empty at this point.
So this is where I'm getting tripped up. So if it's an object, I'm used to thinking of an object as a key value pair, right? So how are we saving this? So we're saying at this index of I, this is the value?
Well, this is a lookup. This isn't, so we're not saving any data
Yeah.
right now. At this point, we're just looking up. We're like, is this data on our object?
Okay.
And so we do a lookup, and if it returns undefined, then we know that we haven't seen it yet. So good question. So this says like, if this is false or undefined, right, we're going to force this into a Boolean. So undefined is going to be false. So this condition is true. Since this condition is true, we're going to enter into the body of this if block. And so since we haven't seen it before, we're going to push that item into our result array. So now our result array has 4, and it also has 2. Can you guys see this on the bottom? And then our cache is empty. We're only here. Oh, I found a bug already. Then we're going to run this operation. This is a constant time operation where we're saving a value to our breadcrumbs object. So array at I is what again? 2. And then we're giving it the value true. That way, when we run into this condition again, we look up 2 in the very next one. So I is now 2. Array at 2 is 2. There's a lot of 2's going on, so our very next one is 2. And have we seen that before? So does array at I, which is 2, what does this evaluate to? We're going to look up on our breadcrumbs object. We see 2 is there, and it's going to evaluate to true. So is it false? No. Since it's not false, we're going to skip this condition, and we'll go to the next one. Yep.
I have a question.
Sure.
So you haven't, you
Can
never.
you speak up just a little bit more?
Yeah, you never push 4 to breadcrumbs, and so it is never true. So if you have another 4, I feel that the breadcrumbs would evaluate to false and then push the 4 in.
Yeah,
right?
absolutely. So that's the bug
Oh, okay.
in our code. Yeah, good finding. So how do we manage that bug? Like, how do we fix that?
We just started I equals 0 and then empty result, all right? No?
Well, that's what we're doing. Oh, I see. So you're saying we could do this? Yeah.
Yeah.
That's
And
another
then
way of
remove
doing
the
it.
array 0 from there.
Mm-hmm. So we could do it that way. We can also just initialize breadcrumbs with the first one in there. Both are good. Cool. Cool. We can do it like that. Oh, but I don't want to ruin the solution for everyone. Okay. So I'm going to keep the bug in there because as I edit these slides, it's going to update them for the later people who use it. Okay, so cool. So then as we go through all these 2's, we already found it. So we're going to keep skipping this if until we get to which index? 0, 1, 2, the third index, which is inconveniently valued at 3, or very conveniently even. So where I is 3, array at I is 3. So then we do lookup breadcrumbs at 3. Does it exist? No, it's undefined. So then we're going to push it to our result, and then we're going to cache it, or simply save that value into our object breadcrumbs. And so this is a way for us to remember and keep track of values that we've seen in the past. A couple hiccups, just like we saw the bug with we forgot to cache the first one. There's also the problem of objects. The keys of an object are always a string. And so it might be wise to JSON.stringify a value before you save it as a key in an object. Otherwise, you can use a different data structure. If you're using ES6, you can use a map data structure where the keys can have different values, not just a string. So those are a couple things to keep in mind with this technique. But this is just a cool way to speed up your algorithms from quadratic to linear. Right? So this is linear because we have a loop. This lookup is going to be constant. This push is constant. This saving is constant in terms of time complexity. This is going to be linear. However, our sorting is a little bit more complex. In sorting, we can think of as n log n in a general sense. We were talking about using the breadcrumbs method to cache values that we've seen before to optimize our unique function. Memoization is a type of caching as well. And so the difference between memoization and the breadcrumbs method is that the value that we're getting to cache, so we did array at I and saved that into our breadcrumbs object, is not the result of a function. If you're caching the result of a function, we call that memoization. And you can think of it as, I think of it as like memorization, we're remembering things. And the concept of caching and memoization are often conflated. Memoization is a type of caching. Caching really, in the simplest form, in a JavaScript environment, is saving something into an object or an array, or even a variable. That's all, more like an object and an array, actually. That's all caching. So if you refresh the page, that's going to be erased. It's not saved on disk. That's caching. Same with Node. If you're going to cache it, you're saving it into an object. It's just on the server. So if you shut off that server and restart it, you're going to lose that cache unless you're syncing it to a database somewhere. So that's what caching is. And then there's types of caching, right? We cache HTTP requests and things in the browser, which is a little bit different execution environment than the JavaScript execution environment. Anyway, we're going to talk about factorial. So factorial is the one where it's like n to the bang. Bang is exclamation point. That's how we say it in programming speak, bang. So what that looks like, so 5 factorial is 5 with the bang, which is just 5 times 4 times 3 times 2 times 1. Cool. So with factorial, we're doing a lot of the same calculations over and over and over again. And so instead of recalculating the result of this, it's actually a recursive function, we could just memoize it, which means we're going to save the result of the factorial function into an object. Just like in the breadcrumbs version, except that the value that we're caching is going to be returned from a function. It's very, very similar. Just where the value comes from is what differs. Cool. And so you can see the repeated here. So it just keeps getting concatenated. And so instead of calculating 36 again, if we just save 35, then we don't have to go through all of the decision trees of calculating the recursion of the factorial.
But Bianca, are you missing when you have pseudocode, is there some kind of code that's supposed to go there? You're just not writing it?
Yeah.
The assumption is that there's going to be code there.
Yeah,
that'll
there's
do the
some code
calculation.
there. It takes away from the point because it's a little confusing. But the point is that factorial of 36 is just factorial of 35 times 36. So instead of every time we calculate, if we already calculated factorial of 35, we don't need to recalculate it all over again, right? Because then we'd have to do 35 times 34 times 33 all the way down to 1. So, do you have a question? Okay. Yeah.
When you talk about caching and memoization, is that kind of related, or could that relate back to space complexity, which you mentioned earlier, along with time complexity? Is this
Yeah.
more an example that this could affect space complexity?
Absolutely. So yeah, with caching, you're always making the trade-off between time complexity and space complexity. So it's faster, but it takes up more space. In the browser environment where a lot of us JavaScript engineers live, it's typically the obvious trade-off is time complexity for us. In other environments where memory constraints are more relevant, it's something that you want to think about more. But in JavaScript world, you can pretty much always memoize, always cache, and it's pretty much always a good idea. Unless you're getting into sort of like big data stuff, then that's something that most of us don't deal with on the day-to-day. So we're just going to jump in. So this is a 3-part exercise where we're going to cache. So my recommendation for going through this exercise is to click this button where it says open it in Replit, or copy and pasting into your IDE, whatever your preferred IDE may be, or your text editor. Open it in Replit, maybe make an account. You can fork it into your own Replit account, and then you could just have a copy of this for yourself. So our first task is to write a function called times 10. It takes an argument n, and it multiplies n times 10. So here is an empty function for you to fill out. That's our very first task. And then the second thing that we need to do is we're going to cache or memoize our results. So you can see in our console log example that the first time we do memoize times 10, we calculate it, right? So we do 9 times 8, et cetera, et cetera. Or sorry, 9 times 10 is the only calculation. We're not doing factorial yet. So just one calculation there. The second time we do it is the cache version. So we already have 90 saved in there. We don't have to recalculate 9 times 10. This is kind of a trivial example where the calculation isn't very expensive. However, hopefully you can see like the larger picture implications of this caching when the operation is very expensive, like factorial, where you have this chain of multiplication that you have to go through. Okay, are you guys ready? Any questions about the task? First thing we're just going to write our function times 10, get a little warm up our fingers a little bit. Then we are going to write memo times 10. It's going to reference this times 10 function. And whenever it has a result, we're going to cache it. It's going to be very similar to your breadcrumbs example. Do you have a question, Kevin? Are you sure?
I just have to look at it longer.
Okay.
Yeah,
It just looks a little overwhelming at first.
Yeah, it's mostly my pro tips. So there's some tips in there. So the first tip is create a function that checks if the value for n has been calculated before. So here it is. You could call it memo times 10. And then inside of that function, if the value for n has already been calculated, has not been calculated, I'm sorry, then calculate it and save the result in the cache object. So the next time you visit it, you can check if it's already been calculated. If it's already been calculated, then just return that value versus actually calculating it. So there's an if conditional in there that says, like, has it been seen already or has it not been seen already? Very similar to your breadcrumbs example where, had we seen that value before, had we not seen that value before? So I'm just going to let you guys take a stab at it. We had 2 tasks. We were writing a function that takes n, multiplies n times 10. Here is our solution for that. N times 10. Our second one was building on that first one, where we're going to use an object to cache the results of our times 10 function. So how do we do that? So we check if n is in cache. If it is, I have a handy console log just for reference here. we're going to just return that value. If not, we're going to say that we're calculating the results. And we're going to calculate it here, right? This is our calculation. We're calling our function here. Versus here, we're just looking it up in our cache. If it's not already in our cache, we're going to call that function, and we're going to save the results of that into our cache. And this is important. We're also going to return that result so that when we're interacting with this, it's actually returning 90 every time, because that's actually what we're interested in. When we're calling this method and we're consuming the method, we want to get the result. So don't forget to return that result. So the first time we call it with 9, it's going to be calculated. The second time, it's going to hit this condition, and it's just going to do a property lookup in our cache. Any questions about this solution?
So there's something that's still not quite clicking with this whole, so I understand the cache is an object, right?
Yes.
So when we did the first function, it's something in the background that's happening, hey, I've calculated this, right? And it's saved somewhere like in this abstract object.
Well, it's
because
happening.
like how do I guess
right
tie
here.
the two together? Like when we say on line 15, if n is in cache, how does that function even knows about cache? Because it's a variable before it. I just like I know it's
Yeah.
kind of a bridge, but I don't know how the two intersect.
Got it. So in this example, we're using this global cache that lives in a parent scope, and functions can reach up into the parent scope, mutate data. It's not a best practice, but it's possible, and we're gonna make it better in the next exercise. So I think the thing that's a little bit confusing to people is instead of starting at the first if condition, let's start at the else, okay? So we're going to call memo times 10 with 9. So memo times 10, whenever we call a function, we're going to hop into that body of the function. In is 9. And in is not in cache, right? Cache is empty at this point. It's initialized as empty. So we run into this else. The first thing that we're going to do is we're going to calculate times 10 of n, which is 90. We're going to save that into results. And here's where the magic happens. We're saving cache of n, so cache of 9 equals 90. Right? Before we were saving our values to true because we were just checking if we had seen it. In this case, we're saving the result of that calculation. So we're doing the calculation, like n times 10 is 90, so result is 90. And we're saving that into cache of n. What is n again? 9. So, and then we're returning the result, which is 90, the thing that we're actually interested in as a consumer of this function. Okay, so that's the first time. Let's go to the second time, and then I'll take your question. I think this might answer your question. The second time, n is 9, and then we're going to say if n is in cache. N is in, so n is 9, is in cache, and what is the value that is saved with 90? So in this cache, we have something that looks like 9, 90. So when we look up 9, it exists. Great. And then we just return cache of n, which is 9, and it's going to return the value associated with 9, which is 90. Questions?
Why are we declaring cache as outside of the scope of memo times 10 function?
Because the second time that we call it, we just need to retain access to it. If we initialized it here, in the way that this is written, every time we recall memoize, it's going to recalculate the cache as empty. So we need to save it somewhere where it's not going to get overwritten as empty, because we're going to initialize it as empty, and then we're going to write to it. And the next time we call it, we execute the body of the function value. We're going to execute the body of the function, which is going to rewrite that cache to be empty. But that's a really good question. All right.
We're never pushing to the cache. Is that what cache with n equals result? Is that what it's
Yep.
essentially doing?
Yep, that's exactly what it's doing. So it's saying, okay, cache, create a property called 9, and save the value 90. And the reason that we're using the bracket notation instead of like cache.in is because in is a variable name, and so when you're going to save a property to an object that's a variable name, you need to put it inside the brackets. And it's going to evaluate what is in, and the environment is going to say, oh, in is 9. Just like we're going to evaluate what is result, the environment's going to say, oh, the result is 90 in this case. So we're going to keep going with this. So the next exercise and you probably saw the sneak preview. There's the solutions, which I don't recommend looking at all the solutions and copying them. That's not a way to learn, but they are available for you, especially for those of you who aren't here in person, to have as a reference. But if you haven't finished the first two, you could just copy the solution from the task 2 and use it for task 3, because we're going to clean up our approach and make this better. Okay. So all right. So task 3 is all about cleaning up our global scope. This task is for our advanced viewers. If you are not familiar with closures, I recommend just sticking with exercise 1. If you have played with closures a bit or you want to take it for a whirl, this is the classic example of when and how to use a closure. And we'll go over it in 10 minutes after this. But so the pro tip here, use a closure to return a function that you can call later. So you can see that we're invoking this function and saving it into a variable name. Then with that variable name, we're calling it again. That's a key aspect of this being a closure. If it was only returning a primitive value and not a function, then you wouldn't be able to call it again. It would just be saved to some value. So it's important that we're returning a function so that we can call it later. And inside of our closure, we retain access to variables that were passed in before, which is a key. So in a closure, you can remember prior values. And if you haven't worked with closures yet, that probably sounds like Greek, and that's okay. Stick with exercise 1. We'll go through the solution, and you'll learn about how closures work. So don't stress about it if that sounds too complicated. Okay, so we're coming back from our third task related to memoization. Our goal here was to clean up our global scope by moving our cache inside of our function. This requires us to return a function from our memoize closure 10 times function so that we could call it later. What this does is it allows us to have a local version of our cache that, one, isn't reset every single time that we call the function that we're concerned about, and it doesn't clutter our global scope. As you can imagine, if you have this global cache and you have multiple functions interacting with this, it can have unexpected results. And so in general, that's why we like to avoid having global caches. And so this is a better approach, is to have our local cache here. But it does require a little more expertise in JavaScript, in particular being comfortable with returning function from functions and then calling them later. So this is called using a closure. And let's walk through how this works. So the first thing we're going to do here is we're going to call this function. It's called memoize closure times 10. Very long name. And what this does is we're going to, since we called it, we're going to hop into the function body. We're going to initialize this cache as an empty object. And then we're going to return this function. So this function now is referenced here. So we can just take a peek at what this looks like. So again, called this function, this variable is just going to save whatever this function returns. Oh, but what does this function return? Another function. Let's take a look at what that looks like. Here's memo closure times 10, which is just referring to our function, right? Which is awesome because that means that we can call it again. But what happens when we call it again? So the first thing that we can do, let's pass 9 to it. So when we call this function, it's important to note that we're not calling the entire body of the memoize closure times 10 folder function. We're actually calling the body of the function that is being returned. This is an important distinction. So when we call this function, we're hopping into the body of this one. Luckily, because of how closures work, we still have reference to variables declared in the parent scope. What is the parent scope? Just this bigger function body. And also anything that's in the global scope as well, we have reference to. So we're going to pass 9. N is 9. We're going to check if n is in the cache. The very first time we call it, we know that we don't have anything in the cache, so this is going to be undefined. So we're going to skip down to our next block. And we're going to calculate our result. So our result is just n times 10. And we are going to save that into a variable, and then we are going to save that value into our cache object, just like before. And then we're going to return the result because we really care about that 90. We're not really so worried about how it's implemented in the back end, on the background. So that's our expected output is always 90, despite whether it's cached or not.
Why would we pass an argument to the kind of parent function? Meaning that, why don't we have like on, I can't see the line, but constant memo closure times 10 equals memoize closure times 10. Why don't we pass something there, and then it becomes an argument in the function it's calling, and then we reference and return that? Like, why does it only goes into the...
So you could do that. So you can pass things here. You know, you can pass numbers here, and then you can call this m, and you can do work on m, and you can also reference m in this function and have access to it, because that's how a scope works, or in this case at least. And so you could do that. The reason that we're not doing that in this case is because we want to create a new function that we can use multiple times. And so this one we can use multiple times, and we'll just pass an in, and the only point of our parent function is to make this cache variable private. That's the only reason that we're doing that, is because we want to take our cache function, our cache object out of the global scope, put it inside of a function, so then it's private to that function scope. Also, what we can do is if we call this again, we can have two separate caches. Okay, so for example, if let's say that, okay, I'm gonna do it. Let's say that we want this to be generic. Okay, and then we would call this memoize closure times m. Okay, we pass m. This one is going to be 10. Okay, following here? So rename this. We're calling it with 10. M is 10. And then we return this function. Now this function is always going to return n times m. So that's what we're going to call this memo closure times 10, because m is 10. However, we could also do something like this. 5. Now, every time we call this function, it's still cached, but we're multiplying n times 5 now. And so every time you call a function, you create a new execution environment, and inside the execution environment, you have your local variables, and you can do really cool stuff with it. And this is the power of a closure, is that you can, even though it's kind of confusing because you're returning functions and there's this other function, it's very, very powerful, and it allows you to make generic functions, and it really is the underlying technique that powers functional programming paradigm. Cool. But we're not doing that. we're just doing like this. So that's kind of cool. And anyway, the reason, again, so the point I want to make here is the reason that we can even call this like this, we have our invocation operator, is because we're returning a function. If you get the error, like, undefined is not a function, then you know that you're not returning a function. I would check what your function is returning and make sure that you're actually returning function and not some primitive value. Or another thing that some people actually accidentally do is they will call the function first and then return that, which is returning the result of the function that's called. Does that make sense? Versus the entire function body. Key here is this is a function definition. This is a function invocation. And they mean different things. One is data, right? So this function here is just data. We can return it like a string. And this is a function invocation. This is an action. So this means run the body of this function, and then afterwards, whatever that returns, you're going to save it here. Anyway, that's our solution. Any questions? Everyone's like, so many questions. Sorry, let me get this in frame. Yeah.
So what would happen, and maybe this would, I just need to know more about closures, but what would happen if you were to do memo closure times 9, 8, and then I just, I'm missing the portion where why does it kind of know that we want 9 to 7 for n if we're not giving it any sort of
We're giving it right here.
Yeah. But then
So we can call, so since this is just a function, we can call it multiple times. And each time, n can be different,
But what happens if you try to do 2 different arguments? Does that work? Or
Like
is
this.
that- yeah.
So if to pass a second argument, you would need to reference it here. So you could do that. It would just be, you would just need to make sure that when you're defining the function definition, that you're referencing that either by passing it, like naming it explicitly, or you could do something like more generic where you're doing like that, where you'll just gather all the rest into an array. That's another technique. Well, I'm going to now talk about our third prompt. So we're going to take the solution from this, and then we're going to build on it a little bit more. So we're going to make our memo function more generic. And let's take a look. So previously, we were either referencing the function outside of the scope, the times 10 function, outside of the scope, where we're calling times 10n inside the body of our function. And a second example, we just did the work directly inside of the function. We said 10 times n. In this case, we want to enable this function to take any function as a callback, and that is going to be the function that calculates a result. So whatever this callback calculates with some value in, or it could be multiple, depending on how you want to do it. But we can stick with one parameter. It's a little bit simpler to get started with. But you can also make it more generic and pass many arguments. So essentially, we need to use a closure again. We're going to return a function. And in that step where we're calculating the result, that's where we're going to call our callback, which is just a generic function that's going to do some calculation for us. And this, in our case, our callback is just going to be the times 10. But you can imagine that it could be really anything. Any questions? I feel like there's questions. Okay, so let's take a look at the other solution, and we can talk about. So our solution here. So our very first solution we are referencing the times 10 function in here, but it's looking up in the parent scope and it's grabbing it. So it's like grabbing out, right? We don't like to do that too much. Similarly with the cache. Outside the global scope, we're reaching out of our function. We want to tidy it up a little bit. So what do? We're going to move our cache inside of our function. So we did that last time. We did something a little bit different. We could still, for the sake of consistency, we could still reference this outside. So the next step is how do we make this generic so that instead of always doing times 10, we could do times 11, right? Being passed in as an argument up here. So you pass something here. I call it CB for callback. Callback is just a function that is passed into a function and then called inside of that function. And so we need to figure out how to make this a little more generic using callback versus using our times 10 function that lives outside. All right, so I'm going to go over all of the exercises in one go from task 1 through task 4, and we'll talk about the different optimizations, and then we're going to go even further and make it a little bit nicer as well. So again, we started off with this times 10 function. All it does is it takes an input and returns that input times 10. It does some calculation here. So when we hit play, we can see we're console logging task 1, and times 10 returns 90. Referencing that. So our second task is to use an object to create a cache so that we don't have to calculate times 10 with the input 9 more than once. How do we do that? Well, first we want to call it with some value, 9, so n is 9. And since our cache is initialized as empty, we skip over that first case and we jump into this else. So in this else, we're going to calculate the result for n, which is 9. And so 9 times 10, that's going to be 90, right? Result is then 90. So cache of n is going to look something like this in our object. So we can move that up here just for our reference. You can imagine that this is happening in the background. You can imagine that's what's happening. And then we return the result. When we call again with 9, it's going to say, is 9 in the cache? And in fact, it is, right? And so we get to jump into this block. We're going to do a little console log, and we'll just return the cache. This is an optimization because we are not having to do this calculation every single time. This is especially important for very expensive function calls. And so we're having a trade-off here of space, right? We're going to be caching all these values, which is adding more data in memory. However, it can really speed up our time complexity. Great. So if we hit play, we can see, let's just clear that. You can see that first, that's interesting. Oh, it's because it already, hold on, I need to. So the cache, since this is the problem actually with having global, oh, that's because I left that there. Okay. It's like it's not clearing. Okay. There we go. So first we calculate the result, which is 90, and then we'll fetch it from cache the second time that we call it. So these are just console logging here and hitting these different cases. Okay. So we have a global cache. We want to avoid that. So how do we clean that up? We're going to move it into a function. We just wrap our regular function in a parent function. We changed this earlier. Forgot what we called it. And when we call this, so we're going to initially call our parent function. It's going to return this function. That means this variable name is retaining a reference to this function. When we execute this function, down here, it also retains a reference to any variables saved or mutated in the parent scope, as well as any variables that were passed in to the initial scope of the parent. In this case, we're not passing anything, so no big deal. But if we had, we could also retain access to those parameters in this scope, assuming that you didn't overwrite it. If you name this in and then this one in, it's going to overwrite it. So just be careful of naming conflicts, but otherwise you should have access. Okay, so then we can hit play. Great. Very cool. All right, and then we have our next one, which is we want to make it generic. As programmers, a big part of going from a beginner programmer to an intermediate or advanced programmer is making things more generic, more reusable. And so with our memoize function, we're making it much more reusable because it doesn't rely, we're not hard coding that times 10 operation. So this function, memoize, which is just called memoize because it doesn't have anything necessarily that it does, you pass in whatever function that you would like for it to run. And so the only difference between this one is we have our times 10, where we pass in. Instead, we just call it callback, we pass in. And when we call this function, we pass in a reference to this other function. So a little crazy. So first of all, we're returning a function. We're saving it in here. But we're also passing in a function, because in JavaScript, functions are just data. We can do that, and it's kind of cool and fun, so why not? And and like I said, since we have access to our parent scope because of closure, we have access to our callback here, and then we just call it right there.
It's already expecting an argument, so that's why we could just pass n right into it.
Mm-hmm. And then we can make this more generic. So right now, this callback isn't so generic, this memoize function, because we can only call it with one argument. So down here, when we call memoize times 10, memoize with times 10, and then we call this memoize times 10 because it's a times 10 method that is memoized. And then we pass the 9. This is going to get memoized and saved into our cache. But we could call this with another function, and it would do the same thing. That's why it's generic, except that we're only allowing it to pass one argument to our callback. So if we wanted to make it a little more generic, you could have it pass multiple using a spread and rest operator, just like that. So then it can be a different variable amount of arguments you can pass in. Mm-hmm.
Yeah, I'm mostly following you, but I'm having a little bit of friction trying to trace the passing of variables through the different functions.
Mm-hmm.
Do you mind doing a trace?
Yeah, absolutely. It's like my favorite thing. Okay, so let's start with, we always start with where the function is being called. So memoize, and we're going to pass that function that we defined up here. Oh, now I lost ourselves. Here we go. So times 10 is now CB. Cache we initialize as empty. We return this function as empty. I'm sorry, it's not empty, it's full of stuff. We return this function. It is not invoked. We just return the body. This check if else is not run yet because we haven't run this function. We're just returning it, the definition. Just like when we define this function here, nothing actually runs until we make it down here and we invoke it. So similarly, this is just a function definition. Nothing is run yet. And we save it in this variable. Now, like any function that we want to run, we're going to call it. We call it down here with 9. So now, 9 is our argument. And so really what this is going to look like is like an array with 9. That's what that args with a dot, dot, dot is doing. Do we have it in cache? No, we don't, right? We haven't called this yet. Cache is still empty. So we're going to do our calculation. This is going to do this. oops, excuse me. This is just going to say like, call back at 9. If there were multiple, like say we did 9 and 10, what it would do is it would just pass it as a series versus an array. That's what that's doing. So we're not doing that, but just so you know. So we're doing our calculation, storing it, caching it, returning it. Then when we get to this line, we're going to call it again. And this is when we're going to hit that cache. So we have 9. Again, we're jumping into the body of this function. When we run the body of this function, all the variables in the scope are going to be reinitialized. But the variables in this scope are going to stay the same. That's very important when reasoning about a closure. The closure variables here stay the same. CB is the same. Our cache is the same. But the arguments that we pass in are new. N is now, well, it's actually still 9, but it's a new version of 9, you could think. So we're going to say, is 9 in cache? Yeah, so we're going to fetch it and return it. Or we're going to console log it and then return it.
Just a question for the else statements. When you create that result variable, does it serve any benefit other than just like readability as opposed to just assigning the cache?
Yeah. It's just there to break out like the step-by-step.
Okay.
So when I explain it, I can
Just
see.
curious if
Yeah. No, good question.
How does the first example greatly differ from the third example in terms of the space complexity and the time complexity?
So for the different examples, the time and space complexity are consistent. In terms of using memoization versus not using memoization in a solution, for our specific case where our callback is really doing a constant time operation, the time complexity improvement is none. However, this technique is really important for when your callback is doing some very time-expensive operations. And so we'll see that when we get later on today, or later on in this course, we'll see as that sometimes our calculations can be very expensive. So in this section, we talked about a couple different techniques for caching, and the things that you should keep in mind when using this technique is that you are trading time complexity for space complexity. So for each operation, you are saving the value, and so you're creating a new data structure and adding new values to that every time. And so you're increasing the space complexity while minimizing the time complexity. And this is really important when your function calls or any operation is expensive. And so usually that trade-off is fine. Often in interviews, people joke like there's like this like optimization question. How do we optimize? And there's a joke. I don't know if people really joke about interviews or algorithms, but people like the thing that people always say is, oh, you just use a hash table. And this is us using a hash table. When they say use a hash table to optimize, this is really what they mean. In JavaScript, an object is essentially a hash table. And in our future course, we'll talk in depth about hash tables. We'll make our own hash tables and all of that. But for what you really need to know in the real world, when they say optimize it by adding, like using a hash table, this is that technique where we're adding things to a cache, which is really just an object, and there are different ways of going about it, but it's all the same concept, which is how do we take an expensive operation and turn it into constant time, or at least linear time, and that is by using a hash table. Our next topic is my favorite, recursion. And so at its core, recursion is just when a function calls itself. However, as you may know, if you've worked with recursion before, there's a little more to that. Recursion is a technique. It's also a mindset. It's a way of approaching a problem with your head, and also You know, you have to feel it in your heart. So hopefully, like we'll wrap our mind around it, and then we'll start to gain some intuition around the recursive technique. And this concept underlies like all the rest of this workshop. So ask questions, slow me down to make sure that we're all on the same page, so that as we move through the content, no one gets left behind. Recursion is one of those things that's pretty abstract, pretty tricky. So, you know, ask lots of questions. I really appreciate it when people do that. All right. So why do we care about recursion? Why do we go through this pain? So it's an elegant solution. It can keep your code DRY, which is do not repeat yourself, which is contrasted with WET, which stands for we enjoy typing, or write everything twice. You know, that's like a thing that you don't want to do when you're programming. And it's expected CS knowledge. And believe it or not, it's actually an easier solution sometimes. And we'll get to a point when we get to trees and graphs, like when it's actually easier to use recursion versus an iterative approach. And here's a common, or I don't know, here's a picture that I like about recursion. So it starts with this question: how many people are in your organization? And then we break this problem into smaller problems. And this guy says, me and all our members of Department 1 and Department 2, etc. And then you talk to the guy in Department 1, and he says, me and all members in Project 1 and Project 2. And then it goes all the way down to just me. So we break down the problem all the way to the simplest case, the base case, where it's just one person. And then you add all of that work up, and you get your result, which is the total number of people in the organization. And so that's sort of like the core concept of recursion. And the way I like to teach recursion is through something called the call stack game. And here are the rules of the call stack game. So the first thing is, whenever a function is called, you push it onto the stack. Then you execute the function body. The function body is like the thing that lives between these parentheses. In ES5 and ES6, then it gets a little crazy when people don't have the parentheses anymore. And then sometimes it's, not these aren't parentheses, I'm sorry. The brackets, and then sometimes it's parentheses. Craziness. But anyway, you know what I mean when I say function body. It's this part. And then you execute the function body until another function is called. Like, for example, this is a function being called inside of a function body. If that happens, then you want to pause the current execution wherever you are and go back to step 1. And you push that function onto the call stack, and you execute the new function body. And then you do that until another function, then you keep repeating it, or until you hit a return statement. If a return statement is hit, you're going to pop the current function off the stack, and you will resume executing where you left off, if you left off somewhere else. So that's the call stack game. We're going to do it in action, because maybe it's not as, so here we have, I can put our rules too. I'll put our rules for us so that we have a reference. So we have our reference on the left, and then on the right we're gonna have our stack. Okay. So here's our function. So as we're executing this, are we hitting any of the rules for the call stack game? We're actually not, because we never get to a function execution. So we have to call this function first. So when we call this function, we push the function onto the call stack, which I want to put over here. Here, let me make this JavaScript for you. Is this big enough? Okay. So we push it onto the call stack, and then we execute the function body until we hit another function, and then we keep doing it. So, and then we're going to keep track of where we left off. I like to use these squigglies. And then we keep doing it. And then we call it here. I'm going to put my squigglies. That is not a squiggly. Put my squigglies. And we're going to keep doing that. In our call stack game, the reason we play this game is this is how your code executes. This is how it's actually executing in the order in which it's executing. And you might see that we're in an infinite loop here. So we keep calling and calling and calling. We're not returning. So this is going to go forever. And it's never even getting to any of these second calls. So we're kind of stuck in this first frame here. And it's never going to make it down here. And so that's really important. Lesson 1 of recursion and just looping in general is you have to return somewhere, right? So let's return.
Isn't it kind of like an infinite loop then, and browser will just
Oh yeah,
say,
it'll just
I'm out of memory.
Yeah. So when you hear the
Overflow.
stack overflow, here's our stack. If we keep going and we run out of memory, and it overflows and it crashes. That's the stack overflow. Next thing we might do to like make this better, we need to throw a return somewhere. Why not? We'll just return here and see what happens. Let's play the call stack game again. So we call this function. We're going to put it on our stack. Great. And we return call me. So first, so this is actually an important point. So first we have to call the function. And then it's going to keep calling it forever. So even though we have a return here, it's still not quite solving our problem. So what we need to do is find a way. For recursion, we really want to be able to loop multiple times, meet some base case, and return up, right? Once we get to, through our questions here, we want to get, once we get to one person, we want to be able to return up and count all of that together. But let's look at another example, see what this is doing. So I'm going to keep doing our call stack game. So we have a tracker here. It's a little bit different. All right, so we need to call it again. And then we're going to pop that function body here. Let's put our global scope too, just to keep track. So we're going to increment this. This is now 1. Is tracker 3 equal to 3? No, so we're not there. We're going to keep calling. So we're going to call, so we hit a function invocation. We are going to, and I'm going to mark this because this is kind of like our global scope. This is our call stack. Okay, so then we're going to increment tracker again. Now it's 2. This doesn't help us. I'm going to go call it again. Increment tracker. It is now 3. We're going to hit this conditional. And we're going to return this value loops. So again, we hit the return statement. What do? We have to pop this off the stack when we need to continue where we left off, which was here. I should have put this. So this function invocation returns loops. However, this function, it has an implicit return. When we reach the end of the body of a function, it has an implicit return. It's going to return undefined. So that's an important thing to note, is that now this is going to return undefined. So if we had wanted loops to be pushed back through the call stack, how might we do that? Let's go back to how we had it. Okay, so we returned loops here. So this one was loops, which is probably what you want to do, right? You want to keep your data. And we pop this off. So what might we want to do so that we don't jump to an implicit return? What's the other option? Implicit, opposite is?
Explicit.
Explicit. So we're going to explicitly return some value. What is that value? The value that this function returns, which is loops. So how we do that is we just stick a return in there. So now and we just assume that all of these are the same. So now when this returns loops, when this function returns loops, this function now also returns loops, so we can pop it off. And this is going to be returning loops. And then we pop it off, which means down here, this will also return loops. So that's the way that you kind of trace the data from some base case and get it out of each recursive call. Do you want me to go through it again? Or do you guys feel solid? So can I see thumbs on how we got loops out?
Doesn't it run forever, though? Am I missing?
It doesn't run forever because we have a return statement. Once you hit a return statement, it's going to exit the function. So we hit this, this return here. Once this conditional is met, this is what we would call in recursion our base case, which is where the very bottom of where we want to recurse to. And this isn't doing anything very important. This is just saying, just recurse 3 times and then return loops. This is what this is doing. It's not doing anything special. And so you can imagine that you can figure out, and this is how we reach our base case, right? So we're incrementing tracker each time we loop. We're getting closer to our base case. If we didn't do that, and we never got tracker to equal 3, then we would also enter into an infinite loop as well. You have a question?
Yeah, so so tracker reaches 3, we hit the return statement, we go back up, pop stuff off the stack. Then if call me gets called again and tracker hasn't been reset, do we just then have an infinite loop and go forever? Because it's never going to be equal to 3 again. Every time we go through, it's going to increment again.
How can we fix that?
We could do it greater than or equal to 3.
Yeah, we could do that. Or
Awesome.
you can just reset it here.
0.
So then next time, we'll just reset it. However, this is dangerous. This is why we don't do globals like this, because you can create a race condition. Weird things can happen. So just be careful. In most scenarios, you're not going to be relying on a global for any kind of loop like this.
Can you do an example where you actually use the anytime in the recursion? Like, how does it work?
Yeah, sure. So let's do one of these guys. This is fun. Okay. So we're going to play our game. We are going to call our function. We're going to put it onto the call stack. What is our in this case is anytime. We're going to increment our tracker. This is now 1. This is false. Whatevs. Or actually, arg in this case, I'm sorry, is undefined. Right? Because we're not passing anything right here. So we start as undefined. However, the second time we call it, we give it a value. But let's put our little line here. So arg at this point is, let me put it in the next line so you can see it, is anytime. We're going to increment tracker. Still not 3. Calling it again, we're going to push it on the stack. Again, this is still anytime. Increment tracker is now 3, which is our base case. We're going to reset tracker. And then we're going to return loops plus arg, which is going to be loops anytime. Hold on, let's get to the, so this is where we were. So let's just pop off properly so that we can see how it loops through. I am putting in this here from where we kind of left off. So we hit this return. Actually, we didn't do this. We never get to here because we get inside of here, we return. This is what we're returning. So let's pop this off. This function is going to be evaluated to what this returns, which again, let's put this actual value. And then, so this evaluates to that. So it's essentially saying, do that. And we're going to return again. So we pop this off. This returns this value. We pop this off. This function is just going to return down here. So that's how you can pass an argument through. You can also start with passing one here as well. But we'll go through more examples. How do you guys feel about the call stack game? Working for you? Mm-hmm.
Can you just repeat one more time why we went from call me anytime to return call me anytime?
Sure. The reason we did that was because in this case, the very first time we returned a value. However, once we evaluated the next function on the stack, it didn't return anything. It just was calling a function. And so what happens just automatically when you don't have an explicit return statement in the function, it just returns undefined. So the subsequent returns up the stack were just returning undefined. And so we were losing our value that we were returning initially. So that's why whatever this returns, we want to also return it. Otherwise, it will just return undefined implicitly.
So essentially, the purpose of this recursion is to continue doing loops until a certain condition is met, and then break out of it and return that value.
Yep, which is what every loop does, right? So recursion is just a super cool way of looping. Hate to break it to you, but that's all it really is. It makes you feel cooler. The typical recipe for recursion is to identify your base case, which is when do you want your loop to stop. So if you're doing a for loop and you say for var I equals I less than array.length, you know, your base case is like I is less than array.length. Like when do you want that loop to stop? Or yeah, you want it to stop when it's greater than, but you know what I mean. Like that's the condition of the loop, and that's your base case. What is your recursive case? So the recursive case is the work that you want to do. Right? So we're not just looping for no reason. There's some work that we need to do for each loop. So maybe we're adding some numbers. Maybe we're doing some other sort of operation. So we need to identify that recursive case, and we need to make sure that each time we call our recursion, we're getting closer to our base case, because otherwise we never meet our base case. We're going to loop forever. And we get into this infinite loop, and it crashes your browser. Nice thing about Replit is that it stops the infinite loop, so it doesn't actually crash your browser, and it will warn you that you have an infinite loop, which is super nice. Because otherwise, if you're playing around with this stuff, you'll have to close and open your browser when you mess up, you know, and you always mess up the first time. So the other thing is you need to make sure that you're returning where it's appropriate, because you can lose your data, as we mentioned. And again, write a procedure that's going to bring your input closer to your base case. And so this sounds all fine and dandy, but applying this to a real problem can be a little bit tricky. All right. So let's look at our fancy loop. Or this is just, this is our recursive loop. So let's check it out and play our game. So like I mentioned, recursion is just fancy loops. And most of the time, I would suggest just using a loop. However, as you grow with your algorithms and data structures, there's going to be times when it's actually way harder to write a solution iteratively over recursively. So it's good to get familiar with the simple cases until you get to a point where, okay, then it's really needed and we're applying it to something a little more advanced. Okay. So we're going to loop, we're going to pass 3. All right, so we're going to push this onto our call stack, emulating how our JavaScript actually would be executing, and we're creating our scope here. Every time we push something onto a call stack, we're creating an execution context. All the variables that live inside of that function have their own little world, and they don't really, you can't, like this when we call again, can't really interact. This parent can't interact with the child, but the child can interact with the parent in terms of scope. You can reach up, but you can't reach in. So I'm getting ahead of myself. So we're passing 3. N is 3. So this will just console log that n equals 3 for your reference. So if n is less than or equal to 1, our loop is complete, right? This is similar to where you say I is greater than array.length. So is it less than 1? No. Okay, fine. We're going to have to call it again, and we're going to decrement n. This is the important part. We need to decrement, otherwise that infinite loop case is what's going to happen. So now n is 2. N is 2. It's not less than 1. Okay, let's do it again. And then usually I like to, in these examples, it doesn't really matter where we leave off, but sometimes there'll be more work that needs to be done after we call our recursion. So it's good to keep track of where you were when you have to go back and do more work. Okay, so now this is 1. Is it 1? Great. Now we're going to return complete. Again, we never get done here because we hit this case, and once we see that return, that means we're going to exit this function, pop it off the stack. Whatever this returns is what this is returning. So this is going to return complete. And let's pop it off the stack. So since there's a return statement, we will return again the value complete. Pop this guy off the stack. And then pop this guy off the stack. So that's our loop with recursion. And through this workshop in this particular section, I want you to get really familiar with translating loops into recursion and recursion into loops. That's the goal. Because loops are easier to reason about. Recursion is just a loop. How do we put those two things together? That's what we're doing. Factorial, we talked a little bit about factorial, and I was like, oh, it does some work, don't worry about it. Now we're going to worry about the work that it's doing each time. So factorial is always going to take the previous result and times it by the next one up. So what does that look like? So result equals 1 times 2, 2 times 3. It's the multiplication of the result times the next thing. So this would be, it's going to take the last one. Let me zoom in for you. So the very first calculation is 1 times 2. The next one is the previous calculation times the next value, which is 3. Take the previous calculation, which is 6, times 4. So 2, 3, 4, 5. And then the first number is always going to be the previous one. So it's going to be just like how it prints. So this is with a loop. This is the iterative solution of a factorial. And then we also have it recursively. And so something to keep in mind is like identifying these patterns. What is the pattern? How is this problem breaking down over time? And you may notice that essentially it's the current number plus the computed factorial of that number minus 1. Right? And let's take a look at how this runs. So returning 5 times the factorial of 4, et cetera, et cetera, et cetera. And this is a classic recursive example. And also, an example that I like to point out is actually easier to just do with a loop. That's my perspective. I think it's easier. Okay. We're going to keep going, these looping things. All right. So here's one. What is this? Okay, here's a couple different ways that we can do it. So we have just our loop, right? Here's a function. It takes a starting point and an ending point. And we're just going to make a loop, and we're just going to log the numbers between some start and end point. So we start at whatever the starting point is. In this case, it's 1. And then we only loop once, really, till we get to 2, which is the end. And we're going to console log that each time. Pretty simple. That's our loop. And here it is using recursion. So notice that we have a function in here. Okay? So we're going to console.log the start and the end. We're defining this function, but we're not calling it yet. Let's play the call stack game. Why not? Let's just do it. It's going to be fun. Okay. Play the call stack game. Okay, so what is this? Okay. Oh, I see. Okay, we're going to call that function. We can focus. So we're going to call this function. Our start and end is going, I'm going to remove our console logs just to give us some space here. So the start and end is going to be 1 and 3. So we're going to recurse on I. However, this function hasn't been called yet, so we're not even going to go there. We're getting ahead of ourselves. We have to wait until we call it. So then we're going to call it, we're calling this function, not this function, okay? So we're going to take that function and we're going to put it on the call stack. We're calling it with our start, which has the value 1. Okay, so I is now 1. So if I is less than end, remember we can reach up into our parent. We keep track of n, which is 3, which is I less than end? Yeah. So then, we're doing it, it's happening again. Let's start keeping track of where we're leaving off before we get lost. So then we need to call that function again. I is I plus 1, okay, which is 2. We can do that kind of math. Okay, so I is 2 in, we're reaching back up. What is it? 3. Is it less? Yes, we're going to do it even more. Okay, and then now we're hitting 3. Is 3 less than 3?
No.
No. So we don't enter into this. We have that implicit return. It's going to return undefined. So this is returning undefined. Right, so we win here. This is returning undefined. Then we continue executing this function from where we left off. There's nothing else going on except that this also implicitly returns undefined. Cool, we pop that off. Same here, implicitly returns undefined. We're going to pop it off. And same, implicitly returns undefined. We pop this off. And meanwhile, we would be console logging hitting index at I. So recursive looping, pop this guy off. Okay, so we're looping. We're looping recursively. We're saying that we need to get closer to our base case. In this case, our base case is this condition. And so these are the kind of patterns you should be thinking about when you're formulating your recursive solution. What is your base case? How do we get closer? What's the work that we actually care about between now and then? All right. So what's the difference between a recursion and a loop? Not really that much. Recursion can always be implemented as a loop, which is fine. It's not necessarily faster, but there are some situations when recursion is going to be a lot easier to implement than a loop, because for some complex data structures with like nested, like especially nested data structures, you don't know ahead of time like how deeply nested things are. And to keep track of that, you would have to use an auxiliary data structure that kind of sort of maps to a stack, but you actually use a queue. And so that's how you would do that. You can do it, but it's just like way more complicated when you can just do it using recursion. And so that's going to be the typical answer to these recursive data structures, like traversing a tree and things like that, are going to be, the standard answer is going to be recursion versus, okay, let's make a loop and then like a queue and all of this other nonsense. So next we're going to talk a little bit about two patterns for recursion. The first one is a wrapper function, and the second is the accumulator pattern. I love my own jokes. So awesome. Okay, so back to our looping. We're going to loop first. This is our original loop, actually. So the loop that we already did, we're using a wrapper function. And in this one, we are just passing our values each time. So let's investigate how this loop works using our call stack game. All right, so let's call, what are we going to call it with? Let's just call it with 1 and 3. So this is like our functions actually being called over here, and then somewhere else inside your execution environment of your browser, wherever you're running your JavaScript, this is happening over there. Okay, so I is 1, and 3 is the end. Okay, so I'm just gonna remove this console log just so that we have a little more space here. So we will start. So this is a lot shorter than the other one, but it's doing the exact same thing. So we are going to check, is I greater than 3? Yes. So we're going to do the thing where we add our function to the call stack because we're executing the function, and we're creating a new execution environment. All of these scoped variables live in a separate world from these scoped variables. How then do we get I and end in this execution context? We get that by passing it in. So what do we pass in? And I'm just going to put our line there. We are passing in I plus 1, which is 2, and then end, we're not doing anything to it, 3. So we're just passing it through, and then so we see I is 2, end is 3. That is still working for us. So we're going to call it again. We're going to add it to our call stack. Again, we're just leaving off right here, just a little reference where we were before. So then 2 plus 1 is 3. Okay, so is 3 less than 3? No. So we have our implicit return. Implicit return, we pop. Again, we're going to finish up where we left off with this line. We're going to move down here. We're going to have our implicit return and pop. We're going to continue here where this line is. And again, this is important if we were doing more work, which a lot of times you will be doing more work in your recursive functions after this line. And it's important to recognize that the stuff that happens after this line, like even though this is the first call, anything that happens after this line is actually happening last. So just keep that in mind.
What's
So
the purpose of this if it returns back undefined, right? So then why are we even doing this?
as a exercise
Oh, okay.
on how we can loop and how we can pass things around and get to a certain base case without having to worry about what is the intermediary step that we need to take and like what is our like big picture problem that we're solving. We're starting with a small problem, which is like, let's just loop and console log some stuff and see how this executes. And then we're going to take this and apply it to some sub-problems, right? Recursion is just all about breaking a bigger problem into sub-problems and in calculating for each loop. Okay, so implicit return pops it off. So this is doing the exact same thing as our other one that we were doing earlier, which is defining a function, calling it here, but we're retaining access to the closure. So one is using a closure with a recursion, and this one is not. That's the difference. Any questions about the difference between these approaches?
So we said the first one has a closure in it,
Yep.
but there's no returning of the function though, right? So
No. Yeah, that's a good point. So this closure is not. So a closure happens when you have a function inside of a function, which in JavaScript land is like all the time. So it's kind of almost silly. However, things get interesting when you return a function that is in a closure. So that's when we can do the interesting thing with the memoize, the generic memoize, is because we're returning that function that has access to closure scoped variables. And so we have this interesting interface where we can interact with scoped variables that are static, and then we can create new execution contexts for our child function. So interesting things can happen when we do that, but you don't have to do that for it to be a closure. Yeah. And so end, for example, the fact that we're referencing end while we're in here is accessing a closure scope variable. Yeah. Cool. But you don't need to know the vocab words, just need to be able to make it work and understand how it runs when you press this play button. This is an accumulator, the accumulator technique. And what we do is, as we build a solution, we keep passing it. So for example, let's do, what do you think I'm about to do? Can anyone guess what's going to happen next? I'm going to play the closure game. I keep calling it weird things. The call stack game. So, oh my gosh, this is a lot of stuff going on, but let's call it. We're going to call join elements. Let's put it at the top. So our array looks like this. And then our join string is this letter E. So what this function is doing is it's going to join this array with the string here. So this array is going to be joined. So array.join is a native array method. So you can join like a list with a comma, for example. That's a common use case for the .join. So if you have a series of, whatever, fruit would be like a common thing, you can do array.join, and then it will say apples, comma, bananas, comma, oranges, like that. However, it's a little bit annoying. It's like a thing that's nice, but it's a little bit annoying because in English we want to put the and in there. So you say apples, bananas, and oranges. And so you may want to write your own like pretty join where it keeps track of when you're the second to last one, and we'll add an and in there as appropriate, with or without the Oxford comma, the programmer's choice, or I guess it's probably like the product person's choice, or whoever's in charge of that, who knows. So we're doing that, except we're doing it recursively, and we're using a technique called the accumulator technique. And let's take a peek at how that works. So we have our two arguments that are passed in. We're defining this function. So we're not pushing this function onto the call stack because we have not called it yet. However, we're going to call it down here. We're initializing it with a couple values. So we're going to call this recurse function. So we're going to push that. So our index is going to be 0, and then the result so far is an empty string. So the first thing we want to do is add the result so far, which is empty string, we want to give it the very first value, which is s. So we're looking up into the parent scope, getting array at index is 0. So we're looking at s. Everyone following where we're getting s from? So now, result so far is s, because empty string plus s is s. Math. Just kidding, that's not math. So if the index is at the end of the array, this is our base case. Did we get to the end? We're going to return. So we're not there yet. Index is 0. So we're going to go into our recursive case. So we're going to return index plus 1 key. We need to get closer to our base case, which is when we have gone through the entire array. We're looping. We're just looping through this array, and at every index, we're giving it a string. Cool. So now we are going to, so this index, so we're going to call this, let's just push it. So we're going to be calling it with index 0 plus 1, which is 1, the result so far, which is our s, and then our join string, remember, is the e. Again, we're reaching up and getting it from our parent scope. Okay. So this is where we left off. This is where we left off before. Oh wait, no it's not. I'm lying too. This is where we left off. Okay, so now we're hopping in. We have these things to worry about. Oh, and sorry, we're concatenating this. So actually, what we're passing is SE. You see where the accumulation is happening? We're accumulating by adding things together, and then we're passing it down into our recursion each time. So now our index is going to be 1. Our result so far is SE. Okay, so what is index at I? We're going to have that one. So, and this is a plus equal, right? So we're going to be building this string out. So we started with result so far, which we passed in, and the next item in the array, which is CR. So now we get secr. Cool. Is index at the end of the array? And this -1, you guys are aware, is because arrays are 0 indexed. That's why we have to do the -1. It is not. So we're going to go into this other case where we're going to call our recursion. What are the variables that we're calling with? Index plus 1 is going to be 2, and result so far plus join string. So here's our result so far, and we're going to reach up and get our join string, which was E, and then pop this on again. Oops, that's not what we're popping on. We're not even popping, sorry, we're pushing this on to the stack. Okay, so our index in this case is 2. Then we have the string that's being constructed. So again, we're going to take our result so far, which is this, and then we're going to add the next one. Uh-oh, a word is appearing, which is T. Are we at the end of our array? Index is 2, array.length -1 is, I don't know, 1, 2, 3, 4 is 4. Or actually it's 1, 2, 3, 4. Yeah, it's 4. So we're not there. And we're going to keep going. And as we loop through this array, we are going to be concatenating our string. And this is the accumulator method that each time after each loop, not only are we incrementing our index, but we're saving some results. And that result is getting passed down into our recursion. So this is some work that's getting done where we are doing some operation, and we're also getting closer to our base case. Cool.
The string at index 3, is that T space COD rather than just T?
Oh yeah, thank you. What could it say? I don't know. So mysterious. Any questions about this? I'm not going to keep going with it because it's going to, I guess, I think, kind of get the picture. The one thing to note before we move on is eventually when we reach this, we're going to return the result so far, which, as you see, is going to be this string that we built up, we accumulated through our recursive calls. And so that will return that, and since we're returning this recursion, this will be returned, and then we'll keep popping and popping and popping until we finally return here, and that's going to return where we initially called it. Are you ready for an exercise? So this exercise is take this join elements function and write it iteratively. So I went through the recursive case, translate that into the iterative case. Okay, so we're going to continue with the solution, and we're going to go through the iterative approach. I was mentioning before that being able to translate between recursion and iteration is going to be key. It's a key concept for dynamic programming. There's a couple different techniques for dynamic programming, and one core pivot is being able to reason about your recursion in an iterative way. So while this may seem kind of repetitive and maybe a little bit easy at this point, this is the foundation of a bigger picture topic that we'll get to in a little bit. So here's the iterative approach. We initialize our results here, and we concatenate it with our join string, and then at the very end we return the result and also the last one. So if you're not careful, if you do this, well, so when you run it, you get the secret code, but just be careful that if you don't do this, you can, it'll like put an E at the end, which is not what you want. It kind of messes up our code, our secret code. So just keep that in mind. There we go. So that's the solution. How many people got the solution? Yeah?
I did one more step. I put a if statement in there. I don't know why I did that for the -1.
Okay. No worries. You guys were able to take a stab at the translation?
Close.
Close. Yeah.
I forgot that there were smiley faces on it, so I printed out secret code, and I was like, I got it. Then moved on to the other one.
Yeah, no worries. So you weren't looping enough. Yeah. Cool. Yeah, I think the smiley faces are probably the most important part of that loop, or that array, so glad we went over the solution, because that would have been terrible. So we're going to hop into our next exercise, which is going to be you writing your own recursive factorial method. You can reference the past slides if you'd like on factorial, but try not to copy the recursive solution. I recommend looking at the iterative solution, maybe looking at the slide where it's like this is the pattern, but not copying directly the factorial solution. You might find that hearing me talk about it feels very different than actually implementing it. So I want to give you that experience of the two differences there. There is a false sense of progress when you hear someone talking about a concept, especially around programming, and it feels like, oh, I got it. The way she explains it seems like, easy, but it's a whole different experience when you have to implement it from scratch and you need to reason through every line of code. So my advice is to not write some code, run it. Write some code, run it, and see what happens, But instead, make sure that you're paying attention to every line of code that you're writing. Maybe even play the call stack game with yourself. I actually do that when I get stuck on something, especially recursion. I play the call stack game with myself just to see that I'm reasoning correctly about how my code is executing. So with task 1, do that. And then if you have time, and for our more advanced people, you can combine this with your memo function that we wrote earlier, and you can memoize your factorial, right? Because the factorial is doing a lot of repeated calculations, and you can just pass it to your memo function, and or you can use your memo function in a creative way to cache your factorial results. So we're just going to hop into the solution here. We're going to call our factorial with the value 5. However, if we check out what factorial is wrapped, it's actually being called with another function. So first, we're passing this function, right, which is just a typical factorial, right? We're doing our work here. Here's our base case. But we're passing it to this function memoize. Let's check out what's happening in memoize. So memoize expects a function. Oh, and it's caching. This looks familiar, right, from our previous examples. So we're going to return this function, and we're just going to call our factorial there. So when we calculate factorial of 5, what happens is we're going to jump in to this function here. So this is going to be 5 in is 5. So we're going to check if it's in the cache. It's not in the cache yet. Otherwise, we're going to calculate it. So we're going to do Fibonacci of 5. I'm sorry, factorial of 5. And then we're going to cache that, and we're going to return that result. All right, great. So let's check this one out. So we're going to do factorial. Oh, actually, sorry, we did not end there. I'm skipping many steps, which is we are going to call this callback, and then we are going to do some work here, and we're going to recursively call our factorial and do our recursive steps. Cool. And this actually isn't doing this. I just realized this is doing something a little bit different. But if we reference this, it's going to be cached, just like in our other example, and we're not needing to calculate it every time. The other thing that we can do is we can cache this line so that we have a check and see if this has already been calculated and cache it. But this isn't what the solution is doing. But that's another way of memoizing this. I'm going to keep going, guys. Divide and conquer, you ready? So divide and conquer is a recursive technique for taking a larger problem, breaking into subproblems, and doing work on each of those subproblems to reach some goal, some solution. And let's take a look at some results. So a classic example of a divide and conquer algorithm is binary search. So Mario here is looking at a sorted list of numbers. Let's say this is 1, 2, 3, 6, 9, 12. There's about 15 or 16 here. Let's say there's 16. And let's say that we're looking for, say that's 10, okay? Without counting each one. So instead of, so we could do, we can go through and look at each one until we get to 10, and that's going to be a linear search where we just go and look at each one. However, since it's sorted, we can break it in half and just search within 1/2. So when we get to the middle, so the first step of divide and conquer is we divide. And then once we get to the division step, we need to decide which direction to go. We don't go both directions because that would be against the whole point of the divide and conquer, where we only want to evaluate half or a part of our data set. So we're going to go to the middle. We can say, is 10 less than 8 or greater than 8? And we're going to say it's greater than 8. So we're just going to throw away the rest, and we're going to go to the middle of the greater than side. So we know that everything to the right is going to be greater than, let's say, 8. And so we're going to go into the middle of 8, which let's say that's like 11 or so here, and it's going to say, okay, is 10 greater than 11 or less than 11? So it's a less than 11, so we're going to throw away all of these things. Again, it's sorted, so we know everything to the right is going to be greater than 11. And then we hop into the middle of the rest of our data that we're looking at, and we find, in this case, that's the answer. But we may even have to do it again, where we say, is it greater than or less than, until we get to our solution. And the reason that this is an important algorithm is that it takes something that's linear and turns it into logarithmic time. How do we know it's logarithmic time? Because the work that we have to do is cut in half every single time. So the data set that we're evaluating for our number is decreasing by half each time. And so that's binary search. Again, binary search has to be sorted. You get an interview question, it says, you have a sorted array, you should be thinking, binary search automatically. Or if they're like, you're searching an array, you could say, well, is that array sorted? If it is, binary search is the way to go. If it's not, there are other searching algorithms, but linear search is a good one, where you just are going to loop through your list and look for that number. So the next bit would be either to implement linear search. So for this exercise, we are going to implement linear search. Linear search takes two arguments. The first one is a list. Doesn't necessarily have to be sorted. And the item that you're looking for. And yeah, and so the task here is to implement the body of this function such that it looks through the array to find the value 90, and it returns the array. All right, so we are going to go over the solution for linear search. I'm going to hop right in. All right, so the first thing you want to do is we're going to need a loop. We can do just a simple, let's do for each, just for fun. So we're going to look at each list item, and we're going to just check if list item equals our item. If that's true, we can return a few things here. We could return the index. We could return true. We could return false. In this case, I'm just going to return the index. So we're going to say var. We're going to say let index equals. So typically when we're doing a search, -1 means that it wasn't found. So as a typical base for not found, we'll just do -1. So that's why I'm initializing the index as -1. So if list item equals item, we're going to need to actually have a second parameter here. So the API for each, when it calls the callback function, the first thing it calls it with is each item. So the first time it'll be 2. And then you can also, it also passes the index. So in this case, for 2, the index is 0. So it's going to loop through. So if the list item equals item, we are going to update our index to the current index. And there's a few things to consider. So if you have multiple 90s in this list, how do you handle that? Do you want to return the first one? Do you want to return the last one? These are things that you should be asking your interviewer, and it's going to affect this conditional here. Make sure you always do triple equals. So In this case, what it's going to do is it's always going to return the last index if there's a duplicate. So just keep that in mind. And that's OK for our solution. We just need to return the index. So if it doesn't find anything, it's just going to return -1.
Bianca, how does it know what the value of I is? It just knows that, hey, since we passed in an array as an argument, I know it inherently will have an index.
So
The I value.
underneath for each, you can imagine like in the internals of JavaScript, it's looping and it's calling this function. And when it invokes the function, it passes 3 things actually. It passes the item, it passes the index, and it passes the list. So yeah, that's just how it works. Yeah. Often, you know, like if you don't need the index, you don't need to reference it. But it's there if you want it. Yeah, exactly. OK. Let's check our solution. 0, 1, 2, 3. Cool. Linear search. Any questions? What do we think of the time complexity of something like this is? Linear. Yeah. Yeah, exactly. Because in the worst case, 90 is always at the end, right? And that would be, you would have to run through the entire array until you get to 90. Now, best case is the first one, and then, you know, it would just do one thing. But we're kind of thinking in worst case, and we're thinking about in general, not for a specific example when we're estimating time complexity. All right. Any questions?
I thought we mentioned previously that the for each and the map were a little bit more complicated. Is this?
They are, in a way. You can consider, so for each is just a loop under the hood. The thing that makes it a little more complicated is that it kind of depends on what you're doing in the callback. So since in this callback we're only doing constant time operations, we're doing a comparison check, we are assigning a variable, those are all constant, we don't have to worry about it. However, if this was doing maybe another loop, if it was doing some recursion or was doing something that wasn't constant time, then that's when it gets a little more complicated. Yeah, good question. So we're going to talk about binary search. Again, binary search is our search where we are expecting our array to be sorted, and we are going to break our list in half every time, and we're going to say, is our value that we're searching for less than or greater than this current location? So if it's less, we're going to go to the left. If it's greater than, we're going to go to the right. All right, what does this look like in reality? All right, so we could do the call stack game with this. That'll be a fun one. And so we just called our binary search with these values. We're going to keep them up here for reference. So we're initializing a minimum. Our maximum is list length -1, which is 1, 2, 3, 4, 5, which is 4. Initializing a guess, that's going to be empty. So while the minimum is less than the max, right? So while we aren't looping outside of the bounds of our function, we are going to grab the center. So our guess is, let's just start in the middle. And this is common for a divide and conquer algorithm. We start in the middle. But if you take a look at quicksort, which we won't have time to cover today, it's not always going to be in the middle. Sometimes you'll pick a point to do a divide and conquer at the end in the case of quicksort, but there's different implementations. However, you can kind of reason that if it's divide and conquer, you're probably going to split it in the middle, although sometimes that's not the case. OK, so is min less than or equal to the max? Sure is. And then now our guess is going to be the second index. OK, so did we find it? 0, 1, 2. No, we didn't. So we're going to go into this else. Is 7 less than 90? Yes. So we're going to increment our min now to 1. And then we are going to loop back into our while. So 1 less than or equal to max? Sure is. So now we are going to math that floor 5 divided by 2. So we're kind of like narrowing the range that we're looking in. Okay. So then that is going to be 2. Did we find it? No. Otherwise, we are going to, so is 7 less than 90? Yes. Then we increment it again. So now this is 2. Okay. Then 2 plus 4 is 6. So now this is 3. So is 0, 1, 2, 3. Then we find it. Okay. Then we find it and we return it. We did it. There it is. Any questions about this?
So if you were dealing with a larger array, instead of incrementing or lowering your guess by 1, you'd want to add the array length divided by 2, and each time
you could do it that way. So you could just divide the length. So you can divide the length, and you can also just say, or you can just choose you can choose an index in the middle, and compare your item to the index in the middle, and say, is it greater than or is it less than? And then you can change your starting index to the one after it. So your minimum. So say your index, you were looking for something that's in the right of your array, so it's going to be greater than your min index. You can just set your min index to that current one. So then the min, and then you can just look in the left. That's another way of doing it, yeah. Cool. So divide and conquer, the idea of divide and conquer is it's a recursive algorithm. We're always going to be working on subproblems. And so the divide part is we break it down in each call. And the conquer part is we're going to do work on each subset. So whether that work means that we are going to be searching for something, searching for a match, or getting it into a correct order if we're doing sorts, which we'll talk about in a bit. And then there's the combine step, which depending on the divide and conquer algorithm, the combine step can look a few different ways. In merge sort, the combine step is really clear, whereas in something like binary search, the combine step is kind of skipped. It's not really a crucial part of the algorithm. So sorting, we talked about a couple different searching algorithms, linear search, binary search. Now we're going to talk another hot topic in the algorithms world, which is sorting. Searching and sorting are pretty time-intensive operations, and they're also core to a lot of the processing that we do in the day-to-day in the web, right? We have Google search, and we want to sort our photos by timestamp and things like that. And you can imagine that when we're dealing with these kinds of problems, the data sets that we're working with can be really, really large. And so there's been a lot of studies done on improving sorting and searching, and we'll be doing a lot of work with that when we get to the data structures part, because a lot of our searching is combined with a particular data structure and how you get to your solution. So if like binary search, right, we have a binary search tree that goes nicely with it. And so we'll keep building on these topics and mastering them together. So for sorting, there are two main types of sorting that we're going to talk about. And we have naive sorts. Naive sorts are going to be quadratic time, right? We're going to compare everything to everything at some point, and you're going to imagine that these are going to have two loops involved. Then we have our divide and conquer sorts. We're going to talk about merge sort today. We're not going to get to quicksort. But these are going to be n log n. So the reason that sorting is always going to have some in, for comparison sorts, there are non-comparison sorts out there that we won't talk about, but you could research those. They're pretty interesting. You always are going to have to compare one item to another at some point. So it's never going to be less, you know, because we have to look at everything, it can't ever be less than linear, right? Same with searching. Actually, no, that's not true. Same with, actually, none of that's true. So for sorting, you have to look at everything. And it can never be like in your head, right? You have to uncover each thing to sort it. So it can never be less than that. But really, the best you can do is in log n, and that's what these divide and conquer algorithms, where we have to look at everything, but we don't have to compare everything to everything else to sort it. Where these naive sorts that's the basis of them. So we have bubble sort. Bubble sort compares adjacent indices and kind of bubbles up the larger number. And so you can see here, we can start with this unsorted. We compare 5 to 1. Okay, 5 is bigger, we swap it. And then we do the next one, 5 to 4, we swap it. And then you keep going and keep swapping and swapping until you can see, like, you can compare 1 to 4, no swap. And you can compare 4 to 2, swap, etc., until we finally reach our solution. So this is a common naive sort. A couple other ones are insertion sort, which you basically take another empty array, and then you choose, or no, this is selection sort, where you choose the biggest one, or you could choose the smallest one, and then you push it into that array, and then you choose the next smallest one, and you push it into that array, and then it builds a new array with the sorted values. Thank you. Conversely, merge sort and quicksort are a little harder to reason about because we are going to be recursively handling the sort. So with merge sort, we take sorted lists. So we have to start with a sorted list, and then we sort two sorted lists. And it's, let me show you the chart. So the first thing you do, you're going to divide and conquer. So let's do the divide step. So we start with an unsorted list. You divide it, and divide it until it's sorted. When is it sorted? When it's a list of 1. So you can assume that any list of 1 is going to be sorted, and so you start there. Then you're going to merge each sorted list. So you're going to choose each one. So this one is now sorted, right? You put 27 first, and then 38, and then so on and so forth until you get your sorted list. And so what this does is you don't have to compare like 27 to 10, for example, until you get down here, and so you're not having to check in like a quadratic way. I wish I had a diagram of how many calls it would be for bubble sort to get to where you need to go. But you can see that we're chopping the problem in half each time. That's going to be your logarithmic part. However, we still need to do like this final loop here, which is going to be like the linear. So you can kind of see how it's cut in half. That's the log part. And then the final merge, you can kind of think of it as the linear part, and that's the n log n of merge sort.
So why do we step through the second and third steps of this tree? Why don't we go straight from the top to atomized into one value apiece and then keep?
Because the nature of recursion. That's why. Because so you could you do that? I don't know. I've never seen a solution like that. That would be interesting. But essentially, you divide it. So you're saying start with a divided part. So the thing about I'll show you when we get to the pseudocode, because I'll show you where it like pauses and then it continues, and then you'll see how this kind of plays out in the code. But I can't imagine it playing out where it's already divided, although that would seem like an optimization if you could. So that's a cool idea. So the merge step, let's just look at this slide here. So during the merge step, we have 2 pointers, which when we say 2 pointers, that means you're keeping track of some sort of index, right? When you're working with linked lists, you're doing a lot of things with 2 pointers. Sometimes that means you have a nested loops, right, with indices being tracked. It also could be you have some variable with an index, 2 variables with indexes being tracked. So that's what, when people say, it's like a common thing people say that just is kind of confusing. So we have 2 pointers. One looks at the beginning of this array, and one looks at the beginning of the other array. And so we ask at each step, which one is less? And so in this case, 3 is less. And we create a new array each time. Each of these steps, we're creating a new array. This is not an in-place sort. And so there's some memory, some space complexity things there to keep in mind. So as we reason through this, so 3 is less, we push 3 on there, and so we slice it. This is gone. So now we have 27 and we have 9. And we say, which is less? Okay, then we put 9. Okay, then that goes away, and now we're still with 27, and we're looking at 10. 10 is less. And then we keep going through that until we build up our final array, and that's the merge step. So this is the conquer part of the divide and conquer algorithm. We're conquering it through this merge step. So what does that look like in code? Merge left and right. Let's look at, trying to think of the fastest way to do this. Let's just pseudocode it right together. Okay, so we went through the logic. Usually I would have you guys do this as an exercise, but we went through the logic of the merge routine. But let's pseudocode it out. So we have a left list and we have a right list. So let's say, what was our example? Let's say is 3, 27. So 3, 27, etc. And then our second list is going to be 9 and 10. We'll just do it a little bit shorter. So 9 and 10. So we're going to compare the first index of the left array to the first index of the right array. Array. Then, actually, the very first thing we want to do is initialize empty array. So we initialize an empty array, and then you want to push the lower value to the empty array, value to empty array, and then you want to like unshift or whatever, shift unshift.
Unshift is the worst.
What? We want to remove the first one.
That's shift.
Shift.
Thank you. We want to shift the, I always get them because it seems like shift, like unshift sounds like you're taking something off. Shift the
original array?
The array with the lower value. So you're going to remove that first one. Then you're going to repeat until both arrays are empty.
In this case, we'll be comparing 9 to 27.
So if we are going to look at it like this. So we have our two arrays. We're going to say is 3 less than 9. We can initialize our empty one here. And we say yes. So we add 3. We're going to shift that. And then we are still keeping track. So we're going to need to be incrementing the indices here. So we're going to keep keeping track here. You can do that with like a while loop. And then we say which one's less, 9. Okay, we're going to push 9 here. We're going to shift that one. And then we find this one. And then now this one is empty, so all we have left is 27. And so this one is empty, and then you would just return this sorted list. And you're going to keep doing that for each height. So you start with just 2, and then you go to 4, and then you're going to do the entire list. And so that's the core, that's the meat of the merge sort algorithm, this merge routine. This is the divide part. So you're going to keep dividing it in half until you get a sorted list of 1. So our base case is when array.length equals 1. So that's our base case. We're going to start returning from that. And once we start returning, so after we return from our recursion, we are going to start doing our merge. So we go all the way down to our base case, and then we hit a return. Oh my goodness. And then we return. And after when we're returning our merge step each step of the way. Here's a visualization you can take a look at. There's also this really funny YouTube video where they're doing like Eastern European sorts, or they're dancing in Eastern European style to different sorts. It's kind of funny. And there's lots of visualizations that you can take a look at. Okay, so here our base case is if the list.length is 1 or less than 2. You're going to break the list in halves. You're going to merge sort left, merge sort right, and then you're going to merge the left sorted and the left right. So let's do our game with our pseudocode. All right, so let's say our list is, I don't know. Okay. So we're going to start with our list. So is the list.length less than 2? Nope. We're going to break it in half. So now we're calling merge sort again on the left side. So on the left side, which if we cut it in half, we can just take these two. So you can do this 7, 6, and then 1, 12. So we're staying here. So remember I said this was important for later. This is why it's important, because we are recursing on the left side, and then we're also recursing on the right side. So we're going to go all the way down to the bottom of our left side. So is it less than 2? 7, 6? No. So we're going to do it again, where we're going to break it in half. It's going to look like this. We're going to have a 7, and then we're going to have a 6. We're going to merge the left side, which is 7. We're going to put our little line here. Okay, I don't know where that 2 came from. Okay, so is it less than 2? Yes, so this is when we return. So now we're returning a sorted list of length 1, which is 7. So this L sorted is 7. Okay? We're good? So we're popping this off. Nothing else is executed because we hit that return. Then we're going to go to the right sorted, and we're going to pause there. We're going to pass in our 6. Pass in our 6 here, which we're just going to return right away. We hit that base case, so we have our sorted list of length 1. Now, we're going to continue, and we're going to merge the left sorted and the right sorted. We talked about how the merge was going to happen, but let's just skip that part and understand that it's going to return these two lists merged in order. So we have 6 and we have 7. We good? We're going to return this. We have a return statement. So we're going to pop this off. And this is going to be our left sorted list. Then we're going to continue on, and we're going to do the same thing with the right side. And in the spirit of completeness, I'm going to go all the way through this example. So the left side, what do we have? We have 1 and we have 12. 1 and then we have 12. All right. We don't have our base case. We're going to call the left side. Okay, so the left side is going to be 1. We're going to return that up because that is our sorted. See, I just think this is genius. I would never, who thinks of this stuff, like a sorted list of length 1? Man. Okay, so then we're going to call it on the right side. And again, we're going to do the same thing. We're just going to return it because we hit our base case. Here we go. We got our sorted list of length 1, and then we're going to merge it in this step, and we're going to return that merged value. So it's going to actually just be the same as what it was. Cool. So we're going to pop that off, and we're going to reconvene where we left off. And now we're going to merge these two. And again, we know that internally this merge routine is going to, pick it and put it in the right order. And so it's going to return 1, 6, 7, 12. And we pop that off, and then that's our answer. Merge sort. Any questions? It's a fun one. All right. So I have some more pseudocode. We can kind of talk about like an algorithmic analysis, just very high level here. We have some constant things like returning and cutting things in half. And then we have our merges, which is we're slicing it in half. And then our merge routine here, where we're looping through the list, is going to be linear. And so we can kind of imagine that to be, or it is, in log n time complexity for a merge sort. So our first sorting exercise is implementing bubble sort. Remember, this is the sort that loops through an array and it bubbles up the highest value each time. And our first task is to implement bubble sort. So I'm going to let you do that. The second task that we have for sorting is to implement merge sort. We went through the pseudocode quite a bit. So just a reminder that we're going to split the array in halves and we're going to merge them recursively. And once we hit our base case, which is a sorted list of length 1, right? So we're going to check for that base case with length is either less than 2 or equals 1. However you want to do it is fine. And then that's the base case, and you're going to start returning up from your recursion. And you're going to compare the arrays item by item, and you're going to return that result. So this is the conquer part of the divide and conquer paradigm. I hope that you took a stab at bubble sort. Let's take a look at the solution. So there's a few different ways that you can implement bubble sort. This first one here is a naive bubble sort where we aren't optimizing for any cases. So with bubble sort, if you loop through an array without swapping anything, that is a sign that your array is already sorted, and so you can just break from your loop. So that's one optimization of bubble sort. And for example, you can see that this solution does not do that. And then we have our optimized version here, where we are keeping track of the swap. So if there is an iteration where we don't swap anything, then we'll just return it. So it's going to short circuit any extra looping when there's no more items to be swapped. So if you're working with a mostly sorted list, bubble sort is actually an okay sort. If you're dealing with a reversed list, then it's terrible. So that's bubble sort. We can check out, when we run it, you can see when we have our basic implementation with the 2 loops, that each time it's going to run it, it's going to run the outer and inner loops the same amount of times. When it's a randomly out of order, it's going to swap it 21 times. When it's already ordered, there are no swaps. And if it's reversed, then it's a bunch. However, when we optimize it, when we go through it, we just loop through it 1 time. And so it's a linear solution if the list is sorted, But again, we think about worst case. And so here's our worst case, which is going to be a quadratic solution. So that's bubble sort. There's a few different other sorts in the naive category. I encourage you to check them out online and implement them for yourself. They're pretty fun. So merge sort, we have our base case here. When your array is a sorted list of length 1, we are going to return that. A couple other things that we need to do is we're going to find the middle. We're going to slice it into a left and right side. And then we're going to recursively merge the left and the right. Previously, we did something like this, where we said, sorted left. This is how we had it before, and I'll put it like that so that it's a little bit easier. So we'll just merge the sorted left with the sorted right, just to keep it a little more consistent with the pseudocode that we were going through earlier. All right. So and here's our merge routine, which we have outside of our defined function. So you can see how we're keeping track of our left and our right indices as we are pushing. We push, we increment, we push, we increment that one until they're all empty. They're both empty. Okay. What else do I want to tell you about this? So the way this executes is exactly as we went over in the pseudocode. Yeah. Here it is for your viewing pleasure. Merge sort. What's the most complicated thing to you about merge sort? Is it the recursion? Is it the merging part?
Yeah. It's the recursion that also calls a different function. too.
So we have like this forking recursion, which is a little bit different than our other recursive examples. We weren't forking, right? So we recurse left, recurse right. Yeah.
I mean, I think hypothetically it makes sense. It's really more the code part of it. How do you, there's just so many detail. How do you keep
Yeah.
track of all of the moving parts? That's where, for me, it's hard to like wrap my brain around that. But I understand how it works in theory when you show
Yeah.
the diagram of it.
Yeah.
It's the implementation that's the
Yeah,
part.
absolutely. And that's one of those things, yeah, it comes with doing this translation from, okay, here's a pretty picture, like how do we translate that into real code? You know, we're drawing boxes, but what does that box represent, you know? What is that data structure? We have these arrows pointing. How do, you know, what does that arrow mean? Is that a function call? Is that a loop? You know, so these are all important things to get some practice on. But yeah, I agree that that's the most complex part for most people, is to make that leap.
And also, what would be the real test case for it, right, or use case for it? Like, when would you like, oh, you know what, merge sort is exactly the solution that I need in this particular instance.
So merge sort is one of the best sorts. So if you ever need to sort anything for an interview, merge sort is probably what they're looking for. Quicksort is what JavaScript uses under the hood. I think it might also sometimes use merge sort depending on the scenario. But yeah, pretty much if you want to impress an interviewer with a sorting question, you can always implement merge sort. However, my interviewing strategy in general is to start with a simple answer, reference the more complicated answer, but not necessarily jump into implementing merge sort. In a high pressure scenario, it doesn't seem, you know, there's a lot of ways it could go wrong and you want to optimize it for things going right. So you could say something like, you know, is it all right if I start with a naive sorting algorithm like bubble sort? I understand that, you know, in a lot of cases it's, you know, quadratic time, and it would be better to do maybe something like merge sort, which, you know, is n log n. However, I think within the time constraints of your interview, it would be easier if I just went with like a bubble sort. Or you can just not even talk about merge sort, implement it in bubble sort, say that you could do better by doing a divide and conquer sort. So like, acknowledge that you understand, you've heard of it, but try to avoid implement. That's my strategy. Just because, you know, if you see, it's quite a bit of code, and there's lots of, you know, like, there's lots of like, you know, you could do off by one. There's a lot of situations where, you know, here's another place where you can go off by one. You know, there are a lot of places where you can mess it up. So I think if you can get away with it, don't do this. But if you're really good at it and you want to get really good at it, then yeah, that would be very impressive to do a merge sort like in an interview. I would be impressed if someone did a merge sort in one of my interviews. But I don't ask those kind of questions. But big companies do.
Ask you what, like give us an example of what people ask you during an interview where you have to use a sort to answer it.
Yeah, I mean, it would just say you have an array of unsorted integers, you know, sort them.
That's just mostly the case, right? They're not going to go like really complex.
Well, so for example, what's a good? I mean, there might be code words for like you have a list and maybe you have timestamps and you need to like order the time. You know, you're filtering by the oldest timestamps. You know, and you know, so like the thing that you're comparing might not be an integer. It could be a date or something. Yeah. What else? Yeah, and I think so there are other scenarios where if your list is sorted, for example, like a binary search, so if your list is already sorted, then that helps you. And so you can always do the JavaScript native sort as well. You just have to remember if it's a comparison sort with numbers, you need to remember that callback, which you do, you call A, comma B, A minus B. Remember that, and then you can get around all of this like raw implementation detail. But there are some scenarios where having a list that's sorted will make your algorithm faster, like for binary search. So if you're trying to search, you say, okay, well, can I sort it first? Once it's sorted, it can speed things up. Or if you get it sorted, that's nice too. We're moving on, guys. Divide and conquer, recursive, break it up into subproblems. Greedy algorithms. It's a little bit of a, greedy algorithms, where do I want to start with this? So, greedy algorithm is just like it sounds. It takes the short-sighted solution, like given a decision, it's going to do the one that looks like the best decision at that time without considering the big picture. So you can think like a toddler. If you say, hey, I give you 1 Oreo now or 2 Oreos later, they're probably going to take the 1 Oreo now kind of situation. Let's see. Usually people teach greedy algorithms like this, but we're not going to talk about it like that. We're only going to talk about how greedy algorithms always make the locally optimal choice. And actually, this is kind of the inspiration for this whole series. And this is an MIT computer science class, and this is one of the classes I took to just online, the open courseware, to learn data structures and algorithms earlier in my career, and it's very very academic, and so this is kind of a response to that. It's like a less academic version. We're just talking about the practical stuff. We're making estimations insofar as it matters to you, like here and now. Maybe one day you'll become like a PhD student and you'll be writing white papers and algorithms, and that's really cool, but this is a good place to start and build up your base knowledge before you take a course like this where you have a bunch of mathematical symbols for something that's at its core very simple, which is, given a choice, they're always going to make the locally optimal one without considering the big picture. So if we have a map like this and say we are trying to get from city A to city G, and these roads between them have different distances. So we have between A and C, we have a road of 3 miles, and A and B, a road of 5 miles. Those of you who have taken a data structures class before, this may look familiar. This is a weighted graph, but let's just talk about it in terms of it being a map. If we were doing a greedy algorithm starting at A, we would say, what is the locally optimal solution, assuming that we want it to be the shortest path? We're going to say 3. Right, so then we're here. Then we're going to keep making these decisions based on the locally optimal solution, which is going to be 4, and then 2, and then 3, and then 4 again. So we come up with this path, which at the end of the day is going to be 16 miles or 16 units, whatever it is. It's a solution, but is it the best solution? No, we can see with our eyes that this one's a better solution. 12 miles instead of 16. However, so this is like one thing that I'm like, greedy algorithms, they kind of suck. And this is one of the reasons. However, there is a time and a place for greedy algorithms, and that's when your data set is so big that you can't think of all of the different scenarios because it's just computationally too much. And so it's better to have a solution than no solution at all. And so that's when a greedy algorithm is good. And we'll talk a lot about greedy algorithms when we get to graph theory on the part 4 of this 4-part series. So we'll get more into that, but let's jump into a greedy prompt. Let's just say that you're a banker in Monopoly. Your family, they just lose all their game pieces, so you need to make sure, so they only have 3 bills. First of all, you have a $5 bill, a $10 bill, and a $25 bill for some reason. And whenever you pay out your family, you want to make sure that you're using the least number of bills, because once you run out of bills, Monopoly is over, okay? So how might you write an algorithm to solve this problem? This is one version of the make change problem, which is the same thing, except you'll see like different versions of this. Oh, Monopoly money, or it'll be coins, or it'll be weight, something like that, where you need to minimize or maximize something. And in this case, we want to minimize the number of coins that add up to our amount. So in this case, it's always going to be divisible by 5, because otherwise it wouldn't work. Okay. So if our input is 40, and we would want an output of 3, right? So it would be 25, 10, and 5. And if our input is 35, it would be 2, 25, and 10. So your task right now is to write a function, make change such that we get the correct result. All right. Good luck. So the greedy solution to something like the make change problem is to simply choose the largest coin that you can at any given time. So if you're starting with 40, you're going to pick the largest one, 25. So you're going to subtract 40 minus 25. What do you have left? 15. So then you're going to do that again, subtract 10, subtract 5. So this is the greedy algorithm, and it seems reasonable, right? It works in this scenario, and for 40, it's going to give us the right answer. And here is how you might do that. You can sort the coins first if you'd like, and then you're just going to do this while loop. While you have a certain amount, you're going to decrement the largest coin you possibly can, and keep going with that. Seems pretty straightforward, However, there's a problem. Would this approach work with these values of the coins? What if the input was 12 and the coin values were 10, 6, and 1? This is where the greedy approach breaks down, and this is why I'm not very pro using a greedy approach in an interview setting, because it can seem like it's correct, but it's also hard to prove that it's correct. And that's just a part of greedy algorithms in general. You kind of have to think of all the scenarios where it isn't correct versus just finding one correct answer and it being the correct answer. With a lot of algorithms, you can just know that. With the greedy solution, you have to say, is the locally optimal solution actually the globally optimal solution? And sometimes it'll feel like it is, and it's not. And so there's a standard, there's this job scheduling problem that is very common when we're talking about greedy algorithms. And there's 4 different ways that you can go about doing that. 3 of them are wrong. So just be aware of that when you're in an interview and you're like, oh, this seems like a classic greedy algorithm. Just know that there's a lot of ways you can go wrong. And so that's why I think we should just do brute force, which is to just go through every different combination of them. And then, when you're introducing, you're like, I'm going to just go with the brute force solution at first, and then we're going to I'll optimize after. It'll be fine. At least you have some solution that's correct. And what's an algorithm if it's not correct, right? I guess in some scenarios it's okay if it's not totally correct. In those scenarios where I mentioned before, where the input size is so big that you can't actually find the correct answer anyway, or you can't really know for sure if something's the correct answer. There's still these unsolved mysteries in computer science. But so for this scenario, our brute force approach is we're going to calculate every single combination and keep track of the minimum combination of coins. So what does that look like? Yes, it's recursion. It is. So we are going to, at every step, figure out all the different scenarios. So the very first step, we can subtract all three. So we're going to go down each of these decision trees and add up the one that is the least. And you can see it's kind of, the depth of the recursion for each decision tree is the same as the number of decisions that are made. So you can see that our best solution is 12 minus 6 minus 6, which is 2 coins. So you can think of it like that. Or we can look at the actual code and we can play our favorite game, which is you guys are going to hate this game after this class. It's so useful, especially with something like this when you have a bunch, you think the merge sort branching, just wait. Just kidding, it's not that bad. Okay, so let's make some change. Maybe we'll just use our example as 12, keep it consistent. So this one is really cool because we have a for each in here. Remember we were talking about the for each making things a little bit more complicated? Here we are. Okay, so we're going to make change. Our value is 12. Oh, this has a recursion counter. I'm just going to take this out. This is just, I have console logs for my examples so that you guys can run them and kind of see some helpful console logs. Okay, so we see our base case. That's when our value is 0. So we're going to keep subtracting our coins from our value until we hit 0. Once we hit 0, that's our base case. We return up. All right, so we're going to initialize our min coins. Sometimes I'll do min coins -1. I think that's better, but that's okay. So we'll just remove I. Okay, so we're going to loop through all of the coins, which we have here. Here are our coins. So for our first coin, we'll start with 10. And we're going to say value minus coin. So here's our value minus coin. It's going to give us 2. So then we call make change here, where our value is 2. All right. So it's not 0. I'm going to initialize this. Again, it's in its own little scope universe. And we have our coin, and then we're going to start with 10 again. However, we don't ever go into this if block because the coin is bigger than 2, or this condition is not met. So we're going to go to 6. Condition is still not met. So we go to 1. Then we do our recursion again with the value 1. And still not there. Initialize that. We're going to start with 10. That's not going to work. We're going to start with, then we're going to do 6. That one's not going to work. Then we finally get to 1. Great. Now we can do, because 1 minus 1 is 0, so it meets our requirements. So, we hit our base case, which is 0. So we're going to return that. We're returning 0 from where we left off. So make change of 0, which is what we just calculated, equals 0. So I'm going to update that value to 0. And then we're going to continue on. So if the minimum coins is undefined, which it is, we are going to enter in here, and we're going to have our minimum coins equal our current minimum coins. So this is now 0. Cool. So then we're going to loop again. Actually, we're going to break through this loop. We're done, because we already looped through all of the values. And then we're going to return min coins plus 1, which is what? 1, yeah. So we're going to pop this off our stack. And this, so make change of 1 equals 1. Min coins, is min coins undefined? Yes, even though we defined it in the previous stack, we popped it off. That doesn't exist anymore. They don't share the state at all. They're separate. So min coins is undefined, and so we're going to set it again. Our current min coins is now going to be 1. So I think, yeah, we loop through everything, and now we're going to return min coins plus 1, which is 2. Pop that off. So make change of 2 is 2. Following? Everyone good? Is min coin undefined? Yes. So we're going to set our min coins to our current min coins, which is 2. And then, so we reached the bottom of one of our branches here. So we did 12 minus 10 minus 1 minus 1. And we recursed up, and now we're back here, and now we're about to go down through the 6. Everyone following how this is keeping track? Okay. Now we're going to, so we did 10. Now our coin is 6. So 6 minus, okay, 6 minus 12 is 6. And so we're going to, sorry, I shouldn't have actually changed that. Make change of 6. So, and as you can see, we are now going here as we subtracted 6. However, the next thing that we're going to do, actually no, this will work. It's going to be perfect. Okay. So we have 6. The first coin is 10. That's not going to work. Next coin is going to be 6. So we're going to make change of 6 minus 6, which is 0. You guys remember what that returns? It's going to return 0. So is min coins undefined? Yes. So min coins now equals current min coins, which is 0. And then we go to the next, loop, which is 1. And now we are, so we already returned here. We're going to go here. And then this goes super deep, so I'm not going to keep going. But the key here is if it's not undefined, okay, which is not, it's 0. That's why it's important that this is triple equals undefined and not something like something like this. This is a common bug. Because if it's 0, it's going to be falsy too. So make sure that it's explicitly set to undefined. Sometimes I do -1 here as well. Instead of checking for undefined, it's going to say if current min coin, which again is just going to be make change of 5, less than min coins. No, it's not. We know that because we have to go through make all of these coins. So 5 is really going to be 5 1 coins. So this is going to be 5, so 6 different coins just to make this branch. And that's not less than 0. I know what you're thinking, wait, but isn't it supposed to be 2? How do we even get there? And it is because, how did we get there actually? I think I skipped a step. But anyway, it's always going to be, as we loop through here, it's always going to be 1 less than what it is. And at the very end, oh, I see. At the very end, we're gonna add 1 up the stack. So we're gonna add 1 because we're gonna go through here. We're gonna do all these calculations, but we're never gonna set min coins to whatever this returns, and that's simply because current min coins is not going to be less than 0. But we're still calculating all of that. So we return min coins plus 1, which is 1 up here, and then min coins. So is current min coins less than min coins? Right, it's 1, yes. So we're going to update this here. This line is updating it to 1. And then, you know, it has to also do all of these, and it's going to go all the way down here, do a bunch of calculations. But it's not going to be less. And so it's going to say, is the current min coins of make change 11 going to be less than 1? Definitely not. So then we get to the bottom, we increment it by 1, and then we have our solution, which is 2. So this is called brute force, and you can see why it is, because it takes a lot of time to go through and calculate every single combination.
How
And
do
so-
you even assess the time complexity of something like this?
It's exponential. Yeah. Yeah. And so given certain data sets, it's fine. You can make it work. However, with even like moderate sized data structures or data sets, it can be too long, which is why sometimes greedy might not be the most optimal or correct solution, but it might be, you know, the good enough solution, a solution for it. So there is our brute force solution. Okay. Yeah.
Where are you making sure that the least number of bills is divisible by 5?
For the different one is not divisible by 5.
Oh, for the one that
The one that we just did, yeah.
Oh,
that
so-
one is just any one, but yeah.
Okay.
For the original solution with the 5 there, I wasn't really checking. I was just assuming, the assumption is all the inputs would be divisible by 5. But yeah, that's a good thing to ask your interviewer actually. Like, should I do a check here, or should I just assume that the inputs are going to be conform to my expectations? And they're probably going to be like, you should probably check for it, because it's not reasonable to expect external data to conform to any sort of expectations. So you kind of have to check those edge cases. That's a good question. So dynamic programming is an optimization technique. We talked a little bit about optimization earlier in this workshop. And we did a couple different caching exercises. So cue that up in your brain, because this is going to build on top of that. And it's also going to build on top of our previous example of make change with all of those recursive calls in a brute force solution. So you may remember that we're doing a lot of calculations, repeated calculations, right, for our make change. I painted this, by the way, because I'm a nerd. We have a lot of repeated calculations. And so what dynamic programming says is if you have repeated, if you can break into the subproblems, and the subproblems are optimal, meaning that they are going to give you the correct answer, you can cache these values just like we did with the factorial, with the memoize for the factorial. That's secretly a dynamic programming solution. And so the reason it's called dynamic programming, which is not really reflective of what it is kind of similar to like why JavaScript is called JavaScript and it has nothing to do with Java. It's kind of like a marketing thing, and these really smart people take advantage of the fact that their management doesn't really understand what they do. And so dynamic programming, they chose the name dynamic programming because it was making some government grant maker more likely to give them funding to continue their research. And then like JavaScript, the reason that we call it JavaScript is because Java was really in, and we wanted to like make it seem like, oh, JavaScript is kind of like Java, you know, we're cool too. So there's like kind of, I don't know, I just think of it as like deceptive marketing to get either like convert people to supporting a programming language, or get someone to give you money so you can keep researching this mathematical concept like as you please. And here we have the name dynamic programming. You could think of it as just caching. If you have a solution that you can cache, that's dynamic programming. So there's a couple ways that you can cache your solutions. So we have a top-down recursive approach, which is what we've been doing a lot of, where we start from, say, 12, right, which is our sort of our end result, and then we break it up into smaller pieces, and we cache if we recalculate something, right? And so that's a top-down recursive technique. And then there's also a bottom-up iterative technique where you can translate the recursion into an iterative solution, starting from the simplest problem, which is when it would be make change 0. So start with make change 0, you calculate that. Make change 1, you calculate that. You cache it. So if it comes up again, you then just have it on hand. So one starts from the top and goes down. The other one starts from the bottom and goes up, and it's iterative. And so that's really the key to dynamic programming is just this memoization step. So all the stuff that you did in the memoization and caching part of this workshop is all related to dynamic programming. And it's kind of intimidating, and I don't think the thing that's intimidating about dynamic programming is necessarily the memoization step. I think the hard part about the dynamic programming is actually the recursion involved in reasoning about these subproblems and being able to trace our minds through how our code executes to solve these problems. And so the way to get through that really is through practicing recursion and better improving your mental model of how your code executes, doing things like the call stack game on your own, or talking, rubber ducking, we call it, where you just talk out loud about what your code is doing. Again, I think an anti-pattern in learning is to type something, hit play, see what happens. We can do that really easy in JavaScript, right? We just refresh, or we hit enter in that console, versus like a compiled language, you kind of have to wait a little longer, and maybe you're less tempted to make these shortcuts. But really being able to reason through what you're writing versus just having your execution environment tell you if you have an error or if your solution isn't what you expect. So, pro tip. What else do I want to tell you about dynamic programming? Question?
Do interviewers, when you are in an environment where they're able to, you're like on a computer doing the interview, do interviewers kind of watch for how many times you try to just run the code instead of understanding
You
what your
can't run the
mistake
code,
is?
actually. So in a typical interview environment, you aren't running the code. You're either writing it on a whiteboard or you're doing it in something like, like a Google Doc. You might even do it in a text editor, but not typically in an environment where you can run it. So it's not that they're not looking for it. It's like you don't really even have that available to you, and so you have to start, you need to learn how to debug your code in your head. And so how you do that is you just choose some inputs. Make sure your inputs aren't too simple, because sometimes the simple inputs can hide edge cases. So a pretty complex input, and run that just like we're doing that call stack game, but maybe you don't really need to do the call stack part if it's not recursion. So that's one way to go about manually debugging. And I think that's the best practice. Even though at first it may seem like a waste of time, it may seem like it's taking you longer to go through these problems, in the end you'll be better for it. Yeah. Cool. Okay, good questions. Any other questions? All right. So the difference between dynamic programming and the divide and conquer technique is that the dynamic programming has overlapping subproblems. So when we're doing make change, for example, there are many times when we're calculating make change of 5. That's always going to be the same answer, versus our merge sort example where that merge step isn't overlapping. Each that has to be done individually, and it's going to change every time. And so that's what I think about when I think about the difference between dynamic programming and divide and conquer. They're still recursive approaches, but one of them has some repeated calculation that you can cache and access, while one of them you can't. You have to just go through it each time. Dynamic programming problems are also really common with really big like Google is really famous for asking dynamic programming problems. So if you are studying to go, you want to work at a big company or something like that, I would focus mostly on dynamic programming, especially because it can be tough to do it within a certain time frame while you're, under pressure. So I would definitely practice these. So how does our make change brute force solution change? How does it change? How does it make change? The only difference really is that you're just caching it, right? So this here, this should also be a red flag. We talked about this. This is global cache. We don't really want that. But to focus on the make change algorithm specifically and not wasting a lot of time talking about memoization techniques that we mentioned earlier and how to make this better. The only change here is that we're going to see if it's already cached, we return. So what this does is, as you're making these recursive calls, you're going to short circuit it each time. And then, what else? Yeah, that's pretty much it. Oh yeah, and you just need to make sure that you cache it every time. So there's like two main differences there. And then of course, you can more responsibly memoize this as well by just passing it to your memoize function, or just adding your cache inside of your make change and returning a function like we did before, and passing in the coins so that you're not relying on this exterior data. You don't want to hard code it. You want to just pass it in as arguments. It's better. We're going to do a quick wrap up here. I'm going to kind of go through the landscape of data structures and algorithms. This is a mind map that I created as I was creating this course, and it's still in progress, but I kind of wanted to give you sort of the big picture of what we've gone over today. So we started off the day with memoization and recursion, which most of these things that are read are recursion, but even some of them that aren't read are recursion. Over here, I haven't colored them yet. So we started with memoization, recursion. Memoization is directly related to our dynamic programming, which we went over the top-down memoization technique. And we also talked about greedy algorithms and combinatorial optimization, which is a fancy word for what we were doing with the make change problem, where you have a bunch of different combinations. You need to find some optimal solution. And what else did we do? We talked about searching. We did binary search and linear search. We went into some sorting algorithms. We talked about merge sort as well as bubble sort. And we talked about them in the context of the divide and conquer paradigm or technique. Some things to look forward to in future classes are some data structure concepts that will be tying into all of these. You can see there's some arrows, and as I build this out, there's going to be more and more arrows. And so when we are working with heaps, we're going to do binary heaps, and it's going to take us to some sorting. When we're doing trees and linked lists, we're going to take, it's going to take us to some searching. Graphs and paths, all related to these dynamic programming and greedy algorithm concepts, as well as all of these things. So these are just some concepts that you covered, some things to look forward to in our next time together in parts 2, 3, and 4 of this workshop.
Are there any specific go-to sites or resources that you recommend for their future endeavors?
Yeah. So I think I like geeksforgeeks.org. I like their content. It's all in Java or C++ though, so you need to. There's not a lot of JavaScript specific content on data structures and algorithms outside of front-end masters, and I think there's one blog that has them, but for the most part, you're not going to find a lot of it in you'll see maybe on GitHub people practicing stuff, but there's no definitive guide. There's a couple books. I haven't been super impressed with any books, to be honest, in JavaScript yet. What else? So I like Geeks for Geeks. I take a lot of the open, like MOOCs. That's like my core go-to. I like Princeton has a good one on Coursera. The MIT one is good. It's just on YouTube. You know, a really good starting one to get the foundational knowledge is CS50 at Harvard, and that's also on YouTube. They have like companion, these little short videos that are like 5 minutes that you can watch, and it doesn't really go into too much code, but it does all the visualization part. So I think a lot of, yeah, I think that's good. If you're interested in like the proofs and stuff, then the MIT course is good. But I don't know. It kind of depends on where you want to go with that. Yeah. Good question. So hypothetically, if I made a data structures and algorithms coloring book, would you be interested in that?
Yeah.
Okay.
Coloring book?
Yeah.
How does that work?
It's kind of like that. You have a question?
Yeah, Aaron Online's asking what the next part of the course is going into.
Yeah. So the next part of the course, part 2 is focusing on some simple data structure, or it's kind of like your baseline data structures. We're going to have stacks and queues, of course, linked lists. We're going to do a hash table, and those are the ones I can think of off the top of my head. We're going to be doing some data structures, and we're going to be combining these concepts with that. So this class is going to be a prereq for the next course, and yeah, and also the other ones as well, because we're going to be applying these algorithms and these techniques to data structures. So yeah, good job, guys. You made it through. That was a lot. Remember one of my first slides where I said, you know, now you know. Now you know. It was a lot. We covered a lot. The next step for you is to just practice, right? So you've heard the concepts, but you're really not going to get mastery until you really have tried these in a lot of different scenarios. But at least you have some concepts that you have some words that you can Google as you approach problems, like, oh, maybe a divide and conquer solution will work for this, and you can reason through that, or maybe I can memoize it or cache it even, and optimize the solution. So you have some words now to start working with, and a foundation in which you can go off into the world and build up your algorithm content knowledge and problem-solving skills. Again, like this, algorithms is something people study for their whole lives, right? And so you can keep going with it, and this is just the beginning. So I'm excited for you as you begin your journey with algorithms, and hopefully we can continue that journey together through the whole Data Structures and Algorithms course here at Front End Masters.
Thank you.
Thank you.